Well, welcome to this course on statistics. As I do for most of my courses, I want to begin this course by setting up what the promise of this course is so that you and me, we are on the same page in terms of what you can expect out of this course. So in terms of the starting point, this course is for absolute beginners. I'm not expecting any kind of prior statistics, machine learning, or any other mathematical knowledge. I will start with very basic, even what is mean, what is average, and then starting to build on top of a little more advanced concepts. And where I'm trying to get by the end of this course, I am expecting that you develop some very good intuition around some of the most popular statistics concepts. And these are the concepts which will not only help you in real life when you try to get a data science job, but also it will help you answer most of the popular interview questions. So the goal here is that as you spend 5, 6, or whatever the duration of this course is, I try to communicate the core concepts in some very easy and very intuitive way so that you develop a good intuition around them and you are able to answer most of them, 70 to 80%, at least 70 to 80% of interview questions related to statistics. I'll try to do it in a very easy to consume and very to understand way. I will try not to include any kind of mathematical equation, and everything will be told and taught through the help of stories and intuition and analogies so that you develop the understanding of the core concept. And later on, even when you go consult and look at mathematical equations, that starts making sense to you because you have understood the core idea. And I believe that in the age of Gen AI, when you have not only Google, but tools like Gemini and Claude and ChatGPT available to you at your fingertips 24/7, there is very little need to memorize the formulas. Instead, what is most important is that first you understand that what are all the tools available, and second, you have developed a good intuition around it. Because as long as you have these two, then any further detail, you can always look and consult any online resources to get further clarity. Okay, so that is high-level promise of the course. Okay, so why you should learn from me, or why I think I'm capable of teaching you these statistical concepts? Well, first of all, I've been working in the field of AI for over 10 years now. And since 2016, I've been working actively in the field of AI. And for statistics, I started learning statistics when I enrolled in BS engineering. So that's 2005. So it's been about 20 years that I've been familiar and I've been learning and I've been using some of the statistical concepts which I've been learning throughout these years. So over 20 years, I've been familiar with this domain. And currently, I am working as a senior staff data scientist at Cisco. Previously, I worked at Meta, Wells Fargo, some of the big names. And there, I have used these statistical concepts, which I've learned over decades now, to solve some real-world problems. I also have a doctorate in AI. I've completed my PhD in AI blockchain. And I've been teaching some of the AI concepts on YouTube, where I have now about 12,000 subscribers, 100 plus videos. So this is basically a long way of saying that I have not only a lot of passion about the subject, I have been learning about it for over 2 decades now, and I have been using them and also teaching them for quite some time now. So to give you a high-level overview of what are all the modules we'll be covering in this course. First of all, there is a very gentle introduction to statistics where we'll figure out why you should even learn statistics, what is the importance of it, how it is relevant to the field of machine learning and AI. So we'll start with that very gentle introduction. Then we'll go a little bit into the descriptive statistics. As I said, I'll start with what is average, what is mean, and then what is the standard deviation. And I'll try to teach all of that in a very easy to understand way through the help of some historical stories, so that I'm not just teaching you the theory, I'm giving you a scenario first, and then I'm trying to teach you the different concepts which are used in that scenario. So the theory I'm teaching you, you have the story reference so that you could make sense on why those concepts are actually important and how they are used in some real life settings. So we'll go over some descriptive statistics, then we'll go over probability, a very important thing, though it is considered slightly different branch from statistics, but they're very related. So usually covered in the same books and in the same courses. Then we'll talk about what are some popular probability distributions. Then we'll talk about inferential statistics and how you can use sampling techniques to get a very good idea about what's going on in the general population. Hypothesis testing, a very important thing which is of immense value when it comes to making some decisions in real life. So it has a lot of significance when it comes to solving some business problems and also some personal problems if you wanted to. Then causal inference. This is one of my favorites because I have spent a lot of time trying to learn causal inference. I think it is a very important and very useful branch of statistics. And we'll conclude by giving you a glimpse of two main school of thoughts in statistics, which is Bayesian statistics and frequentist statistics, and how they are different and what is the usefulness of both of them, so that once you go out of this course, you have a very good idea about what are the different concepts and what are different school of thoughts which are used in statistics. And as I said, the main purpose of this course is that you should be able to answer most of the interview questions which are related to statistics. So at the end, I have gone through some popular interview questions which are related to statistics so that I can go over them with you and I can help you understand those questions and give you a sense of how you can answer them in the interview settings. And even when I'm going through each of these chapters, I'll try to include 2 to 3 sample interview questions so that whatever theory you have learned through the lens of a story which I have told you, you can also see that what kind of interview questions you can expect out of what you have learned and how you should be answering them. So that is the high-level overview of the course. I'm very excited to embark on this journey with you, and I really hope that you find this course not only very enjoyable and easy to consume, but also useful so that you could use these learnings to answer some real interview questions. Okay, so let's start with our first module about introduction to statistics. And especially for people who are new to statistics and have never taken any statistics course before, I'll try to make this intro section very gentle, very easy to understand. And I'll try to teach whatever concepts I'm teaching through the lens of a story so that it's easier to understand. So what we are going to cover in this module, we'll start with Netflix prize story. It's an interesting story which happened about 20 years ago. So we'll go over that. Then we'll define statistics, why it's useful, what are its two main branches, and then we'll understand what are different types of data, and then how statistics can help you answer some real questions at a high level. Okay, so there is a lot to cover in this module, so let's get started. So the main story we are going to teach in this module is $1 million reward offered by Netflix in the year 2006 to improve their recommendations. So Netflix, if you don't know about Netflix history, Netflix is a relatively old company. Previously, they used to rent out movie DVDs. So people would request a rental of DVD movie. They will get the DVD by post and then they have to return it. And then when the online services became prevalent, Netflix started its streaming service. And in 2006, when the streaming service was still relatively new, Netflix realized that their main asset is not just their movie library, but also if they could give recommendations to the people on what kind of movies they should watch, that would be a gold mine, because then based on that recommendation, people can watch other movies. And if they like those movies, then they would trust more of those recommendations, which eventually means that there would be more business for Netflix. So Netflix internally had a recommendation engine, but they launched this competition that they would give $1 million to the winning team as long as they improve their current recommendation by at least 10%. And this we're talking about 20 years ago. $1 million is a lot of money even today, and it was a lot of money back then. And this event sort of became a worldwide event where researchers and data enthusiasts from all over the world started competing in this competition. Big companies, big research labs of big universities, and even individuals. There were a lot of people who were competing in this competition. I won't bore you with more details, but the ending was very dramatic. The winning team, they submitted their solution just 24 minutes before the deadline, and they won by 0.0001% as compared to the second best team. So a very interesting story overall, but the key takeaway is that data can possibly predict something as nuanced and something as personal as human taste. And this is what the power of data was in 2006. It has further improved now. And if Netflix is spending $1 million on this prize, they would definitely be getting a lot more out of this competition over the last 19 years. And if this is how much they could have got back then, and if insights from data can get this kind of ROI back then, it can definitely do much better now, as we have a lot more data, a lot more compute power, and much more sophisticated algorithms available. Okay, so what is statistics anyway? Well, I have searched for many definitions, but the best one I found is that statistics is the art of making decisions. It is basically that statistics helps you make good, wise decisions based on data. That is what statistics is. And if you look at statistics from this lens, what could be more useful and more fun to learn than this science of statistics? I still remember that the first time I heard the word statistics, I was in 11th grade. And in the mathematics course, there was one chapter on statistics. This was my first intro to statistics. And our math teacher back then, even before he started teaching the chapter, he started building a lot of enthusiasm around what he's about to teach. And he said that he's going to teach us something on that day, which will help us make decisions for the rest of our lives. And he portrayed it in such a way that it is almost magic, that based on data, you can make some decisions which are very intelligent and also much wise as compared to gut-based decisions. So statistics, in a nutshell, this is the art of making decisions. The key function is that you take raw data and then you turn it into useful insights which you can use for those decisions with the power of statistics. And it's not just about math, it's about problem solving. Because in real life, as you are dealing with actual problems and actual data, it is hardly ever the case that you realize that this is the data available, and then you apply this statistical approach, statistical formula on top of that, and you get something useful out of that. It is hardly ever the case. It is mostly that you first have to understand what is the business problem. Then you try to understand what could be different hypothetical solutions for that problem. Then you see what does the data say. Then you develop a lot of hypotheses and then you test those. So it is a lot of back and forth. It is very similar to a detective work rather than just plug and play of some formula to get the insights. And I think this process of problem solving is what makes this science of statistics not only very useful, but also very rewarding and very pleasing to practice as well. I would highly recommend this book, Thinking in Bets. It's written by Annie Duke. Annie Duke is a former poker champion. And in this book, she outlined that how you should use statistics to make real life decisions. And she was coming from the background of poker, and she explained the stories on how you can use the data which is present in front of you and some basic statistical concepts to make decisions which can not only be useful in the field of poker, but also in a lot of other real world problems. I think this is a very interesting read if you want to see that how statistical thinking, statistical mindset can be used to make intelligent decisions in real life. Another reason you should definitely learn statistics is that it is the backbone of data science. Any AI, ML concept which you are trying to learn, it has most likely its foundation in statistics. So statistics is the foundation on which the house of data science and most of the decent and sophisticated algorithms are built. And by learning statistics, you can become someone who is not only using the latest and greatest ML AI tools, but you're also familiar with their inner workings and have a good intuition around how these algorithms actually work. So this is definitely one of the reasons you should try to learn statistics. Also, it is a superpower because it helps you ask the right questions. By using statistics, you can infer some good insights out of the data and you can ask the right questions. Also, it provides some guardrails around what kind of decisions you should be making, what kind of mistakes you should not be making. It will tell you that when you should believe in data, because as we are going to cover in some of the modules, just because something is coming across as legitimate out of the data just does not mean that you should blindly trust it. There are a lot of landmines which you can avoid once you have developed a good intuition and understanding of statistics. So let's talk about the two main branches of statistics. One is descriptive and the second one is inferential. The main difference is that descriptive is about the past. Whatever data you have available in the past, how you can make most insights out of that, that is about descriptive statistics. You can summarize and describe the data's feature. You can answer questions like what is the average rating of Batman in the Netflix movies data. Now, when it comes to inferential, this is about future. So based on the past data, because we never have future data available to us, based on the past data, you can make predictions about what's going to happen in future. And that is when statistics is almost similar to magic, because this used to be the domain of magic and psychic to be able to tell what's going to happen in future. But statistics helps you do that. And then the example for that is that you can predict your rating for some movie which you have not seen yet. And then there are countless other examples where based on the historic data, you can make some very solid predictions about the future. So since statistics is all about data, let's look at what are different kinds of data at a high level. And we need to have some sort of differentiation between data types, because the way different statistical and machine learning algorithms use data is different based on what kind of data it is. So at a high level, there are mainly two data categories. There is numerical and then there is categorical. Numerical is anything which represents quantities. For example, 1, 2, 3. Time is also numerical. How much movie you have watched is also numerical. So all of these are numerical data types. For example, movie rating, movie runtime, as we talk about Netflix movies data. And then in terms of categorical data represents groups or labels. For example, the genre of the movie, or who is the director of the movie. Is it a movie or is it a TV show? All those kind of groups and labels, they come in the form of categorical data. And the reason we have to distinguish between these data types is that because based on what kind of data it is, the different kind of treatment it gets. For example, when we are talking about movie ratings, we should know that this is a numerical data type, and that means that 2 is greater than 1 and then 3 is greater than 2 if it is movie rating. And when it comes to categorical data, we would know that, for example, horror genre is one category and then comedy is a different category, and there is no relationship that horror is worse or better than comedy. It's just these are two different categories of data. So we talked about at a high level, there are two data types, numerical and categorical. And within those, there are further subtypes. So within numerical, there is discrete numerical and then there is continuous numerical. Discrete is something which you can count. For example, 1, 2, 3. It could be episodes you have watched. It could be anything which can be represented as whole numbers. And then continuous something which can take any value within some range of value. For example, the exact movie runtime. It could be 2 hours, 43 minutes, and then 0.1 seconds. Similarly, within categorical, there are two categories. There is nominal and then there is ordinal. Nominal is that when the categories have no logical order. For example, if the genre is comedy or if it is horror, nothing is superior or better or worse than the other. Whereas in ordinal categories, there is a clear order. One category is better than the other category. And the example could be that if we have 5 categories of movie ratings, which is 1, 2, and all the way to 5, then 1 is lower than 5, and similarly 2 is higher than 1, and there is a relationship between these categories. It is very important that you have some understanding of these data types, because as I said, when you are going to feed these data into different machine learning algorithms, when you are trying to get some insights out of that using any statistical tool, you need to know that what kind of data type you are dealing with so that you could deal with it accordingly. Okay, so we are at the end of this module. I hope that I have not touched on to anything which is scary, which is difficult to learn in this intro to statistics module. So very quickly recapping what we have covered in the module. So we defined statistics as the science of making decisions and the science of learning. We compared descriptive statistics and inferential statistics and how they're different. Descriptive is about past, inferential is about future. Then we classified different types of data, and then in the next module we are going to touch on a very interesting historical story on how Jon Snow, who was basically a data detective, used the power of data to save human lives. Okay, so in this module we are going to look at some of the essential things about descriptive statistics. So at a high level, what we'll be covering in this module is that we'll look at the 1854 London mystery of cholera outbreak. What were the popular thoughts about the reason for that outbreak, and then how John Snow, a physician, used the power of data to figure out what the real cause was. We'll see that what are the measures of center and spread, how we can mathematically calculate that at a high level. We'll see that how we can visualize data with charts and plots to get some useful insights out of that. And through the story of John Snow, we'll see that how describing data can solve some important real life problems like saving lives in the case of 1854 London cholera outbreak. So what happened in London in 1854? London was a busy city even then. We are talking about more than 150 years ago. And a crisis happened. A disease spread, which started taking a lot of lives. There were a lot of deaths happening in the city of London. And the popular belief at the time was miasma theory, which basically means that through bad air, a disease is spreading, which is taking life. Now, a physician named Dr. John Snow, he was skeptical of this miasma theory. He thought these deaths are not happening as a result of bad air. And he had a hypothesis, and his hypothesis was that this disease is spreading through contaminated water. Now, he had this hypothesis theory, but he had no way of refuting this popular miasma theory that the disease is spreading through bad air. And he had no way of proving that it is actually the contaminated water which is leading to this cholera outbreak. So he needed some data, and he needed to do some analysis on top of that data to make a point that his theory that this disease is actually spreading through water is true. So what he did was very interesting, and it was very innovative at that time. So instead of just making a ledger of who died when and making a table out of that, John Snow said that how about I start putting each death on the map of London to see that where most deaths are happening. So he went door to door to figure out that everyone who died, what was their location, how many people died in each building, in each street. And based on that, he created some dots on the map of London, and that is called ghost map. And this was very interesting because this was one of the first representations of a technique which we call scatter plot now, where we scatter some data points across different axes to see where there is a concentration of more points. John Snow created this ghost map. He took the map of London and he started marking wherever the deaths were happening. And based on that, he realized that most of the deaths were happening around this Broad Street area. And he realized that on the Broad Street, somewhere around here, there was a hand pump. Most of the people who had died had consumed some water from that hand pump. So John Snow, based on this, had now a concrete evidence that the deaths are located in this area, and a possible culprit is a hand pump which is located in the center of Broad Street. He made a recommendation that the handle of this pump should be removed so that no one else consumes that water. And as soon as that was done, there was a significant reduction in the number of deaths which were happening because of cholera outbreak. And this further solidified the theory which John Snow had been propagating, that the disease is happening because of the contaminated water. And when people stopped drinking water from that hand pump, the spread of the disease significantly got reduced. And this is the power of scatter plot, which is one of the most fundamental data science charting technique. Okay, so we saw that how Jon Snow plotted some dots on the map of London to figure out that what the center of the disease is. But what about if we have to mathematically calculate it? We have a couple of ways in figuring out what is the center of any data distribution. So in this case, since it is a two-dimensional chart, we have vertical axis and then we have horizontal axis. One option is that for each of these vertical and horizontal dimensions, we figure out what is the center. For example, vertically, we can see that this is the center, and then horizontally, we see that this is the center. Then we figure out that this is actually the center in the two-dimensional space. But to make things simple, let's say if we just want to find what is the center of a data distribution in a one-dimensional space, let's say we are just talking about the broad street here, then we have a couple of ways of doing this. The easiest and the most intuitive is the mean. It is similar to what we call average. It is a very commonly known technique in figuring out what is the center of a data distribution. Let's say if we are just talking about Broad Street and we have different buildings in Broad Street. Let's say we have building 1 to 10, and then we figure out that there is one death which happened at building number 2, one death at building number 3. There are 2 deaths at building number 5, and then there is one death at building number 10. So one death at building number 2, one death at building number 3, 2 deaths at building number 5, and one death at building number 10. If we want to calculate the mean, which is actually the average of this, then we just have to sum up all these numbers. So it will be 2 plus 3 plus 5 plus 5, because there are 2 deaths happening at building number 5, and then plus 10, and then we have to divide it by the total count, which is 5 in this case. One of the drawbacks of calculating the mean or average is that it is usually very sensitive to outliers. So if we have another building, which is, let's say, building number 1000, and there is a death which happened there, you will see that the average value will significantly go way beyond because of the presence of this outlier, which is building number 1000. So another approach we have is calculating the median. This is basically we order all the deaths and then calculate the middle. So we again put all these deaths in order. So it will be building number 2, 3, 5, 5, and then 10. And then since this is the center or the median value, we'll say that this is the center. The other option is that we calculate the mode, which is the value which is most frequently happening in the data. Again, in this case, we can see that since 5 is present twice in this data, so that will become the mode value. Again, these are some of the ways in which you can calculate the center tendency of the data. And as you have seen in the example of Jon Snow, that is very crucial in analyzing some patterns out of the data. And even if you cannot visually look at the data like Jon Snow did, even if you have just the longitude and latitude of all these death locations, you can use any of these techniques to find that what is the center of this disease, and then based on that, you can find some insights out of this data. Now, we have figured out a mathematical way, actually a couple of ways in figuring out what is the central tendency of the data. Now let's figure out how we can find the variability in the data. And variability is important because, again, going back to the example of Jon Snow, if you have figured out that this is the center, you need to know that all the deaths, are they concentrated around the center? And if they are dispersed, how much they are dispersed? Because if all the deaths are centered around the center, that means that there is really something going on. But if there is a lot of dispersion, then the finding of the center might not be very valuable. For example, even if the deaths were equally distributed throughout the city and you had figured out that this is the center, it would have been of no meaning because the dispersion in the data is just so much. So how can we mathematically calculate the dispersion or the variability in the data? There are a couple of ways. Let's again take small toy data sets. Let's say if we have a couple of numbers, we have 2, we have 3, we have 5, and then we have 8, and then we have 12. We have these 5 numbers and we want to calculate the variance or the variability in the data. The first option is very simple, do that we just calculate the range of it, which is what is the smallest and what is the lowest. We know that 2 is the smallest, 12 is the biggest number. So the range is 10, where we are just minusing 12, 2 out of 12, which is 10. So we know that the dispersion of this data is 10. Then there are some advanced techniques. One is that we calculate the variance, which is basically we first figure out what is the mean or average value of it. So when we calculate, we know that the mean is 6. And then we try to figure out how much far each of these numbers are from the central value, which is 6. So let's say if this 6 is the middle number, then we know that 2 is a little far on the left, then there is 3, then there is 5, and then 8 is a little far on the right, and then 12 is further right. So basically we calculate each of these distance from the center. The thing is that if we just calculate these differences, then these would be minus numbers and then these would be plus numbers. To make all of them positive, we take a square of all of these numbers. So it is square of all of these numbers. In that case, all of them become positive numbers. So this is what variance is. The next step is standard deviation, where we are just taking a square root of this variance, because variance was taking squares. So it makes sense to take a square root of that to further normalize it. And then standard deviation basically becomes the average difference from the mean value of each data point. So again, the numbers here would be, so it will be, in case of variance, it is difference is 4. So we have to take a square of 4. Then in this case, the difference is 3. Let me take a different color for this. So it is 4, 3, and then 1, and then 2, and then 6 here. So basically you take a square of these in each case, and then we add all of them up. So that gives us variance. And whatever variance number we get out of this, if we take a square root of that, then that becomes standard deviation. Now, another approach which we take is that of calculating the interquartile range. So that is basically we figure out what is the bottom 25% and what is the upper 75%, and then we take a difference of it. In this case, the bottom 25% is the average of these two, which is 2.5, and the above 75% is the average of these two, which is 10. So then the IQR becomes 10 minus 2.5, which is 7.5. So these are all the ways in which you can use some very basic mathematical formulas to calculate whether what is the central location of the data, but also how much far apart it is spread from the center. And using these two informations, you can draw some very important insights out of the data, as John Snow did for the London's case of cholera outbreak. Now let's take that story even further. John Snow did not do it, but let's say if you are interested in knowing that how fast the outbreak is growing, one option is, which is a very popular option, that you take a period over which you count the deaths. A very logical bin in this case could be a day. And then you figure out how many deaths are happening in that bin. Let's say if you figure out that on day 1, there were 5 deaths, on day 2, there were 7 deaths, on day 3, there were 9 deaths. Then let's say on day 4, there were 14 deaths. Then you can visually represent this data in the form of a histogram. Histogram is very simple. You basically have 2 axes. This is your vertical axis. This is your horizontal axis. On the horizontal axis, you have all these bins which you have defined. It could be a day, it could be a week, or if it is a different kind of data, it could be totally different kind of bins. But let's say if the bin is 1, 2, 3, 4, these are the days. And then on each day, how many deaths are happening? So you plot, this is 5, and then this is 7, and then this is 9, and then this is 14, which is even bigger. So you can represent these numbers on a chart, and by just looking at it in a glance, you can clearly see that the trend is upwards, and with time, more deaths per day are happening. This will give you a sense of if the problem is increasing over the period of time, or is it decreasing, or maybe it is steady state. And if it is increasing or decreasing, what is the speed of change in this case? So the previous analysis of finding the central tendency and the variability in the data gave you an idea of where the problem was happening. And this kind of analysis can further tell you that if the problem is worsening or improving, or maybe peaking with the period of time. Okay, so far we have seen how we can find the center of the data. We can find how we can find variability. Then we also saw that how we can use scatter plot and histograms to find some important insights out of the data. These are a lot of things. There is one chart which is used by most statisticians, which will give you a 5-number summary of a lot of important details, so that you don't have to do a lot of these analyses, and within matter of seconds you can see what's going on with the data. It is called Whisker box plot, and this is what it looks like. So it gives you a couple of data points. One, it gives you what is the median value of the data, so you see what is the median. Second, it gives you 25th percentile and 75 percentile data, and as we know that the range in between is called interquartile range. So it tells us what is the center of the data. So this is the center. And then this is what the spread of the data is. And then it has find some maximum and minimum value, which are calculated using this formula, which is Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. So these are the maximum values and the minimum values. And then it shows you the outliers graphically, which are falling either above the maximum value or below the minimum value. Generally, it is a very insightful, useful box plot, which you can use to look at a lot of information in a very smart, in a very easy, and in a very fast way. One caveat, though, is that it is generally considered not a good chart to represent in any executive presentations, because there's a lot of technical jargons like interquartile range and how are we defining the maximum and minimum value, all of that. So it is good for statistical consumption, but when you are reporting the data to some high-level executives, it is usually not considered a good plot to represent, but I still wanted to call it out because if you are internally doing any analysis on any data, this could be a chart which you can plot using modern Python libraries within a matter of seconds, and it'll give you a very good idea about what's going on in terms of data distribution for the data you are interested in looking at. All right, so we are approaching the end of this module, and we covered a lot. We described that how you can find not only the central tendency, but also the spread of the data. We also figured out that how you can unearth some important patterns in the data visually, with plots like histogram and box plot. We also talked about scatter plot, which Jon Snow created. And then we solved that how by describing data, you can find some very important real world problems which have far reaching consequences, like cholera outbreak of London. Now, in the next module, we are going to see that how we can use these findings and extend them further to actually predict the future. And that is when we'll be talking about a very interesting concept, which is probability. I'll see you in the next module. Welcome to module 3 of this course. In this, we are going to discuss a very important concept related to statistics, that is probability. So in this module, we are going to start with a very interesting story about a World War II statistician and how he made a very counterintuitive finding which helped save a lot of lives. So in our previous modules, we have been thinking how we can find some descriptive statistics about the data we have seen. Now we are going a little bit advanced into the realm of thinking about the data which we have not seen yet. So we'll touch on some two very critical, very important concepts of conditional probability and Bayes' theorem. We'll also touch on central limit theorem. These are some of very interesting and very important interview questions as well. By the end of this module, you would have developed a good intuition around probability. How do you think conditionally about probability? And a good grasp of important interview questions like Bayes' theorem and central limit theorem. We have a lot to unpack in this module, so let's get into it. So let's begin with the cornerstone story of this module. So the story is about World War II. In World War II, US was sending some warplanes into Europe, and a lot of those planes were, of course, getting hit by enemy bullets, and a lot of them, of course, did not come back. So US, let's say, is here, and then this is the start of Europe. We're just sending the fighter jets, and a lot of jets are going, but some of them are not returning back. And they were not returning back because they were getting hit by the bullets. One solution they found was that there was a protective armor which could protect the planes from getting hit by the bullets. But the issue was that that protective armor was very heavy. So if they were to install that protective armor throughout around the plane, then the plane would become very heavy. It won't be as fast and it will take a lot of fuel. So this became a very classical optimization problem. And they asked a lot of statisticians to come and suggest which areas they should be covering with the protective armor. Now, a lot of people started giving a very common sense solution that of all the planes which are returning back, you inspect which areas of the plane have received the most amount of bullets, and then you start putting the armor around those areas. So let's say if this is a plane, now it has some critical areas. For example, here we think is the engine and cockpit. And then there are non-critical areas, for example, the tail, the wings, and maybe the nose area as well. So the common sense approach to this was that you inspect all the planes which are coming back, and then you inspect them on in which area they have received the most amount of bullets, and then you start putting the armor around those areas. But a very seasoned statistician, Abraham Wald, had a different idea about looking at this data. Wald pointed out that there is a problem in the general approach which most people are taking. That is, they are only studying the survivors. And the key question is that where are the bullet holes on the missing planes? Because these are the planes which got hit so hard that they were not able to come back to the US. And his idea was that we should put armor where the returning planes have no holes, because it means that the bullets are received in some very critical area that the plane was unable to come back. And these are the areas where we should be putting the arc around. And this is a very classic example of a known phenomena in statistics, which is survivorship bias. The key idea is that in a lot of cases, we are just studying the survivors and drawing wrong conclusions out of that data because we are not looking at the other data which is missing, and that is the data about things which have failed. A very common example is that I hear a lot of people which go to some of their favorite restaurants, and of course these restaurants are very busy, and the conclusion everyone is drawing is that we should start a restaurant business because all these restaurants are super busy and they are making a lot of money. The issue is that when you are thinking about restaurants, you're only thinking about restaurants which are very popular and which are very busy. You have no idea and you have no data about a lot of other restaurants which open up because no one goes there, they ran out of money, and then they ran out of business. But just because we see 40, 50, 60 restaurants which we know are very popular, which we like, and are also very busy, making a lot of money, we think that all restaurants make money, but we do not have that other side of the data of the failed restaurant businesses. Another example of survivorship bias is that when we are looking at the stories of successful founders like Steve Jobs and a lot of other people, we might draw the conclusion that dropping out of college is actually a very good idea because a lot of these successful founders of big tech companies, they dropped out of college. But the data which we are missing there is that look at all the people who dropped out of college and then what happened to a majority of them. Most of them, I can bet, did not make a very good living. But since in the case of survivorship bias, we are only looking at the stories of Steve Jobs and Mark Zuckerberg and alike, and that is why we might wrongly draw the conclusion that dropping out of college is a good idea, because if you drop out of college, that means you can start a very good, thriving business, which is clearly not the case. So Abraham Wald's insights seem very interesting and very logical in hindsight. Let's look at it closely to see, was it just a lucky guess? To prove and understand why he was right, we need to look at the language he was speaking, and that was its language of probability. So before we go a little deep into it, let's cover the very basics of probability. Probability is represented as it's a number between 0 and 1. And you can think about, and if you multiply that by 100, then you basically get the probability of that happening in percentages. And percentages are generally a little easier to understand for our mind. But whenever we are putting this number into some numerical calculation, it is a number between 0 and 1, where 0 means impossible. There's no chance that is going to happen. And then 1 means it is 100% guaranteed that this will happen. So 0% probability of happening, it means there is no chance. 100% probability of it happening is that it is almost guaranteed. And then event is what we are talking about happening, and then the outcome is what actually happens. For example, if you are rolling the dice, then the event is rolling a dice, and the outcome is, let's say, if the number on the dice is 1, 3, 6, whatever. So these are some key terms which we'll be using when we are talking about probability: event and outcome. And the example is that when you say probability of head on a flip of a coin is 0.5, which is 50% when you multiply it by 100 to translate into percentages. And also the probability of tails, if it is a fair coin, is also 50%. So this is like a very, very bare bone introduction to probability and introduction of some key terms. Let's now look at conditional probability, and that's where things start becoming a little more interesting. So now let's talk about conditional probability. So we now know that simple probability basically means that what's the chance of something happening. For example, in the case of Abraham Wald story, what's the chance a plane gets hit? Or when we are rolling a dice, what's the chance we get a 6 or we get a 1? Or when we are flipping a coin, what's the chance that we get a head and a tail? So that is simple probability. In mathematical terms, we just represent it as probability of event, let's say probability of A. Now, the conditional probability is what's the chance of something happening given some condition, and that's why the word conditional comes in. So we say, what is the probability of something happening given we have some other information already available to us? For example, what is the probability of a plane returning safely given it was hit in the engine? So now you can see that how Abraham Wald might have thought about this problem in mathematical terms using the language of probability and conditional probability. So generally it is written with the notation of probability of P given A, probability of P of A given B. So this straight line in the middle is read as given. So it's instead of probability A, it is probability of A given B. In the case of Abraham Wald, for example, he would be calculating probability of survival given hit in engine and probability of survival given hit in wings, for example. And this is a very important notation which you will be seeing again and again as you open up any probability book. What is the probability of something happening given we know something else? And this is a very important concept as well because probability changes with the new information. The context of the problem changes how we calculate the probability. Let me give you a very simple example to demonstrate this. Let's say if you have a test for a disease and that test is usually considered 99% accurate. So you got tested for that disease. The test is 99% accurate generally, and you got positive, let's say. Now, that means that your probability of actually having the disease is 99%, right? Because the test is 99% accurate and you got positive result. But now let's say you get some new information, and the new information is that the disease we are talking about is very, very rare. Now, in that case, your probability of actually having a disease is not 99%. This is what we're going to unpack a little later in the module. And if on the other side, we say that the disease is very, very common, pretty much everyone has it, then your probability of having the disease might actually be 99%. So this context of how much prevalent the disease is changes this probability of actual disease as we introduce some new information into it. So that is why the context is very important, and that is why conditional probability is very important, because whenever we are calculating some probability, we have to add some prior knowledge, some prior conditions into it so that we are calculating the right statistics. How do we do that? We have a magical theorem which helps us do that, which we're going to cover next, and that is called a Bayes theorem. So Bayes theorem is one of a very important concepts in statistics. It is also a very common interview question as well. And here I just want to lay out the idea, give you an intuitive explanation around it. Hopefully it will make sense. And the reason it is very important is that, as I was saying, it helps us calculate the probability of something happening given some condition. Now, there is a mathematical equation for it. I can write for you here. But again, the main idea I'll be focusing on is that how do you develop an intuition around it? And we'll briefly touch on a non-mathematical way of actually calculating some numbers as well, because plugging in numbers into mathematical equations sometimes it's a little difficult. So I just want to emphasize building an intuition around it since it's a very important concept. We start with a prior belief. So in the case of Abraham Wald, it is what is the probability, let's say, of survival of a plane. So this is, let's say, what we generally think is the probability of survival. Then we collect new data that were there any bullet holes in the plane? Was it hit in the engine? Was it hit somewhere else. So we collect the new data, and then based on that data, we update our probability, and this is called posterior probability. So post data collection probability, and prior is prior data collection probability. So you have an initial probability, you get the new data, and then you update that probability, because again, remember conditional probability, something happening given we know this, given we have this data. So that is what the process is. And it is very common to use this in a lot of cases. Sometimes even when we're not thinking about this, we are using the same process. For example, if I've lost my keys, what is my initial probability of where I can find the keys? For if I say, okay, maybe I left it in the bathroom, or maybe I left it in the pocket of the dress which I have taken off. The initial probability distribution, let's say if I say it is 30% is left in the bathroom, 60% is left in my pocket, and 10% somewhere else. So that is my prior probability. Now I receive some new data. Let's say I go look into the bathroom, and now I see it's not there. Now, based on this data, now the probability distribution will change. It won't be, because I've cut out that 30% part, that it's possible that it is in the bathroom. And whatever new calculation of probability is, that is my posterior probability. A very good example of that is that if you are watching any kind of match, be it cricket match, be it anything, you see that in a lot of cases they show you what is the probability of this team winning versus the other team. And that is your prior probability based on all the information you have previously received. And then as the match begins, if it is a cricket match, for example, at every ball, whatever new information gets presented, based on that, at the new probability of who is going to win the match keeps changing. And it changes on every single ball, because on every single ball we get some new information. How much score every team is making, how much are they left behind from the target score. So that is what Bayes' theorem is, that you start with the prior probability, you get some new data, and based on that you keep updating your probability. Because probability is not a static thing. It's not that the probability of something happening stays constant. Every time you see something new information, you have to update your beliefs on how likely the outcome is. Now let me write down the equation of Bayes' theorem briefly, but again, you don't have to memorize it. I'll try to explain it more intuitively. So you can calculate probability of A given B if you have probability of B given A multiplied by probability of A and then divided by probability of B. So this is the formula. But again, we'll be talking about it at a more intuitive level. And as I said, more information, more context around the problem, it changes how you calculate the probabilities. Going back to the example I introduced in the last slide, that let's say if you get tested positive for a test which is 99% accurate, then what is the probability of your disease if you do not have any prior knowledge? Probability of disease is going to be 99%. But what happens if you know that the disease is very rare? So again, we can plug in some numbers into this mathematical equation, but let me try to explain to you another approach, which I think you should be taking, and that is called frequency counting approach. That I think is more intuitive and easier to wrap your head around as well. So the approach basically is that instead of plugging numbers into the equation, you just at a high level start with some very big number and then walk yourself through the process. So we say that we have a population of 100,000 people. And since we know that the disease is very rare and it impacts only 1 in 1,000 people, that means there are only 100 people who actually get the disease, and there are 99,900 people who did not get the disease. Now, if we test all of these people, since the result is 99% accurate, 99 people will test positive. So these are the people who get positive result of the test. Again, since the test is 99% correct and all these people do not have the disease, still 99 people will get the positive result, because these are the 1% people who got the incorrect result. So now in total, we have 99 plus 999. In total, we have 1098 people who get the positive result. But we know that only 100 people have actually got the disease. But we have 1098 people who got the positive test result. So if the disease is this rare and you got a positive result, your actual probability of having a disease, given that this disease is this rare, for this calculation is about 9%. So it's not, if you get positive test result and the disease is rare, your probability of actually having the disease is just 9%, not 99%. But if pretty much everyone is getting that disease and then you get a test which is 99% accurate, in that case, it will totally change your probability of having a disease if the disease is common. That will be totally different. So I hope that at a high level, you now have some idea on what is Bayes' theorem, why conditional probability is important, what at a high level Bayes' theorem's working is that you start with a prior belief, you get some new information, and then you update your beliefs. Now let's talk about another very interesting example of Bayes' theorem. So there is a very interesting example of Bayes' theorem. It is called Monty Hall problem. And there used to be an American TV show, and its name was Let's Make a Deal. And Monty Hall was the original host of that show. And based on that, this problem is associated. And when we look at the literature, it is interesting because this exact problem was sent to American Association of Statisticians in around 1977. So a very common and a very interesting problem. So in that game show, Monty Hall, who was the game show host, used to show the participants 3 doors. So let's say these are the 3 doors. Now he would tell the participants that 2 of these doors have goats, 1 of that door has a car. So the participant has to pick one door, and if there is a car behind it, the participant will get that car. Now, of course, everyone wanted the car, and that's why they were participating in the show. The key here was that once the participant takes their initial pick, let's say if the participant took this gate, let's say gate number 1 and 3, and let's say this is gate number 2. So Monty will say behind gate number 1 and behind gate number 3, there is one might have a car. And to make things easier for the participant, he will open up one of the doors. Let's say he opens this door and there is a goat or a sheep behind this. And this is the door which the participant has initially picked. So the question or the option Monty will give to the participant is that, do you want to switch the gate to this one or keep their initial choice of gate number 2? Now, one way of looking at it, again, this is like a very common sense way of looking at it, is that all these gates have 1/3 chances of having the car. And even when Monty opens up this gate, the other 2 doors still have 1/2 chances of having the car. So it doesn't really matter if the participant sticks to their initial choice of the door, or they switch the door and come to the other door which Monty has still not opened. So that is a very intuitive and general common sense way of looking at it. But what statisticians argue is that the probability argue is that they should change the door when Monty gives them the option of switching. And by doing that, they are increasing their probability of opening the door with a car behind it 2/3 instead of 1/2. So let's figure out why it is. So again, we have 3 doors. So this is door number 1, door number 2, door number 3. And the initial probability is 1/3, each of these having a car behind these doors. And let's say the participant picks up this door. Now Monty comes in and he opens up this door and shows there is a goat behind this door. And he gives them an option of staying with the door number 2, which is their initial choice, or changing the door to door number 3. So now what statisticians argue is that once the participant initially picked this door, there is a 1/3 chance of the car behind this door. And there is 2/3 chance of the car behind some other door. And when Monty opens up this door and shows there is a goat behind this door, then that option gets eliminated. So all this 2/3 probability of having the car behind some other door comes to this door. That's why there is 1/3 chances of having the car behind this door, which is the initial pick, and 2/3 chances of having the car in this other door. So in all cases, the participant should switch the door and pick the other one, which Monty has not picked. Again, this is an example of how you think about things with probability and conditional probability, and how new information, for example, Monty showing a goat behind one of the door, changes the probability distribution, and based on that, you should update your posterior probability because you have now some new information present. Okay, so far we have been talking about the probability of some individual event happening, the probability of having the one individual having a disease or not, one plane getting survived if it gets hit in the engine, etc. But in most practical scenarios, we are not dealing with single probabilities. We are dealing with thousands of them. And that is when the central limit theorem comes in. It is a very critical, very key concept of probability and statistics, and also a very popular interview question. And a lot of people argue that it is something which is so powerful that it feels like magic. And this theorem is the bedrock of statistics because it helps us make a lot of statistical inference and helps us do hypothesis testing. All of that we are going to cover in the upcoming modules. But a very important concept for you to understand. So before we go into it, let me try to give you an example scenario. So let's say that your task is to calculate what is the average height of males in the US. So now US has a very big population. And of course, you cannot go and measure the height of every single person or ask them what their height is because you have about 320 million people. It's difficult, almost impossible for you, especially for you to figure out what the height of every single person is. So in that case, you have to rely on a sample. You have to pick few people, and then based on that, you have to make some conclusion. So your task is find average height of US male adults, let's say. And the answer you should get back, and since you won't be able to measure the height of every single individual, you have to rely on some sample. And the answer which I want out of this is that you should be 95% confident that this is the average height of a US male. Or you can give me a range as well, that within this range is the average height of US male, and I am 95% confident. So this is the outcome we are seeking. So again, the task is find the average height, and the end result which I want is that you should be 95% confident that this is either the height of the average US male adult, or this is the small range within which a range would lie. What central limit theorem says is that you have a team of 25 people and everyone goes out and measures the height of different people or asks them what their height is, and then they get 100 records. And then for each of those sample of 100, you calculate an average. So let's say person 1 comes back and then they tell you that their average is 5 feet 6 inches. The person 2 comes back and they tell you their average of the 100 people they asked about their height is 5.4, and so on. What central limit theorem says is that if you plot this distribution, it will always be a normal distribution. What is a normal distribution? Normal distribution is something like this, a bell curve. We are going to study more on different kind of distributions, but at a high level, this is what normal distributions is. It is also called bell curve because it looks like bell. So this is the center in which it has the highest height, and then as you go towards the side, it goes down in height. So this is the bell curve. And what central limit theorem says is that this distribution, if you plot it, it always follow this bell curve. So in this case, person 1 has 5.6 as the average height, person 2 has 5.4 as the average height, and let's say person all the way to person 25, this person requires the average height to be 5.2. Now, if we plot all the people having the height of, let's say, 5.4, then let's say there are 5 people from this list of 25 who said that their average height is 5.4, and then there are 3 people who said that their average height is 5.2, and also 3 people who said that their average height is 5.6, again 3 people, and let's say 1 person on other side who said that average height is 5.1 and 5.7 in this case. So this, if you plot it, then it follows a normal distribution. So the key thing about central limit theorem, again, the name implies that central because it follows a central tendency. This is the center. Limit is that as your sample size approaches to infinity, you would see that your bell curve starts becoming small and small, approaching towards the center as your sample size increases. And the reason this is a very important and a very cornerstone theorem in probability is that even if the underlying distribution is not normal, even if, for example, you have a roll of a dice, now the outcome of having 1, 2, 3, 4, 5, 6, all of them is the same. So it is a uniform probability distribution. But if you take an average of 10 dice rolls, and then what is the outcome? And then again, some 10 dice rolls. Whenever you start taking the average of the samples, it always follows this bell curve. And the reason it is so powerful is that because it follows the same pattern of the curve, it helps us define some hypothesis testing. Because as we study the properties of the bell curve, we know that something falling between this period, it has 95% confidence, for example. So we can talk about hypothesis testing, and we can answer this kind of question that what is the 95% confidence interval that within this range, the average lies of the actual population. So even if you do not fully understand this, at a core level, the idea is that if we have a very large population which we want to survey and which we want to understand, we cannot do that in most cases because we just do not have enough resources. So the technique we resort to is that we take samples. And whenever we take a lot of samples, and for each sample, we calculate what their average is, and we plot it on this chart, it always follows normal distribution. And because it follows normal distribution, and normal distribution has some essential inherent properties, we can do some hypothesis testing on top of that, and we can come up with some very strong beliefs about what is the confidence interval within which we think the actual average of the whole population, which we did not have resources to find their property values, we can still use central limit theorem to find out where their average actually lied. Now, to show that to you graphically, let's come to this website. So here it lets you pick some distribution. So this is uniform distribution. Let's say we have skewed left, we have skewed right, we have normal distribution, which we now hopefully are familiar with. So let's say if we pick a uniform distribution, here it is telling you that the average value here is actually 200. and then the standard deviation is 115. Now, if we take a lot of samples, and for each sample, we have a size of 2, let's say if we calculate that, then it says we have taken 20,000 samples, and then for each of those, the sample size is 2, and this is what the distribution looks like. Now, let's say if we increase the sample size to 9 now, you can now see that 1, it still has normal distribution. Second, it is approaching towards the center. It is becoming squeezed. Let's go to the n is equal to 25. You can see it is further approaching towards the middle. And that is what central limit theorem means, that as the limit approaches infinity of this sample size, the distribution is approaching towards the center. So n is equal to 36. Again, you can see that it is becoming more squeezed, approaching the center. At 100, again, even more squeezed, approaching towards the center. And again, a very important thing is that the underlying distribution was uniform. It was not a normal distribution. But what we saw here is that the sample average distribution is always normal. Again, let's look at some other distribution. Let's say skewed left. So this is the underlying distribution. Again, starting with n is equal to 2, we can see that it is roughly a normal distribution, and it is very wide. Let's say if n is equal to 9. Now it is clearly a normal distribution, and it is approaching towards the center, becoming more narrow. N equal to 25, even more narrower. N equal to 36, further narrower. N equal to 100, again very narrow. And again, that illustrates the point. Regardless of the underlying distribution, whenever we take sample averages, it always have normal distribution, which means that we can do a lot of hypothesis testing on top of that. Again, a topic to be covered later. But the important thing is that as the sample size keeps increasing, that curve you are seeing, it starts approaching towards the center. That is why the name of this theorem is central limit theorem. As the limit approaches infinity, bell curve starts shifting towards the center. And that is what all this theorem is about. So we covered a lot about probability, conditional probability, Bayes theorem, central limit theorem in this module. I wanted to briefly explain to you some initial origins of the probability theorem and how it sort of got developed. So the initial traces of discussion about probability, we find that in 17th century, gamblers wanted to, of course, win more. That is true. That was true then. It is still true. And they wanted to understand that how they should fairly divide the stakes in a game which is still unfinished. So if the game is finished, of course, it is very understandable that based on the original terms, who should be getting the reward. But if the game is unfinished, then we are talking about chance of someone winning. There is a this % chance that this team or this person will be winning, some other % chance of someone else winning. And they wanted to ask that. So initially, a French nobleman, they reached out to this mathematician, Blaise Pascal, about this query, that how they should be distributing the stakes in the unfinished game. And then Pascal started having some correspondence through letters with another mathematician, Pierre de Fermat. And this correspondence happening through letters is the initial documentation we had around probability theory discussion. And this whole science around probability started developing. And it's interesting that how something as fun and as trivial as some game discussion can lead to a development of a complete new mathematical science. I initially referenced you towards the book, which I really like, which was Thinking in Bets by Anne Duke. And again, she is a poker player. She was a poker grandmaster. And she was talking about in this book that how you can use the probabilistic thinking and thinking in statistical terms in making some decisions which helped her a lot while playing poker. And the same rules and the same learnings can be applied in making a lot of other decisions related to other matters of life. Okay, as we are approaching towards the end of this module, I wanted to cover some of the important related interview questions so that whenever you see them in the interviews, you know that what these questions are about. And we have since freshly covered them. I hope that the memory is still fresh in your mind. So one, a very simple and very popular question is asking about survivorship bias. Now, the question could be in the form of explain what is survivorship bias, just because they want to confirm if you have heard the term and you have some idea about it. And it could be a case that they give you a scenario and then say, what is wrong with that? I gave you an example of looking at the founder's profile and then thinking that maybe dropping out of college is a good idea. So they can give you that kind of scenario and then say, okay, what do you think is the problem in this approach? So then you have to highlight that you are talking about survivorship bias, and we have a lot of missing data in this case, which we are not consulting and looking at while arriving at the conclusion. Another one is conditional probability. Again, very popular interview question, and it could have different formats, but the essential thing remains similar to the idea which I explained of, let's say, if the test is 99% accurate, but we know that the disease is rare, then if you test positive, what is the visual probability of actually having the disease? Again, Bayes' theorem in work. And actually, I have seen that there are a lot of interview questions related to Bayes' theorem. So if you have developed a good intuition around it, and you know the counting frequency method, then that really helps you at least go through the problem in your mind and having developed some intuition. Again, since it is a topic from which a lot of interview questions come, I would encourage that you try to find some more questions around Bayes' theorem and then try to see that how you can use Bayes' theorem to help answer them. Once you have solved like 5 to 6, maybe 10 questions, I think that is enough. Okay, another important interview question around concept of central limit theorem, why it is useful. What is central limit theorem? What does the name central limit theorem applies? All of these questions are very important and very frequently asked. And then some case study. So they'll give you some scenario, and within that, you have to figure out if there is a Bayes theorem relevant, if they are talking about some central limit theorem tendency, and then how you can do some hypothesis testing on top of that. And then maybe some scenario in which survivorship bias is relevant, and they want you to point that out. So these are some popular interview questions which are asked related to this module. Again, I think two very important things we covered here, Bayes theorem and central limit theorem. They are very commonly asked, mainly Bayes theorem. So I would encourage you to do some exercising independently out of this module as well. And then towards the end, in the last module, I'll also cover some important interview questions, again, to give you some idea about some other ways in which the questions can be asked about this. One popular interview question for Bayes theorem is there is a Seattle rain problem. So I would encourage you to Google that to see that how what kind of question it is, and I'll try to also cover it in the final module of this course. Okay, so it was a long module to cover. We covered a lot of important things here. We talked about survivorship bias. Then we started thinking about probability using the Abraham Wald story of World War II. That what is probability, and then how do we think about conditional probability? And then from conditional probability, we started thinking about Bayes' theorem, that how do we update our beliefs as new information gets presented. So we covered all of that. We talked about central limit theorem, why it's important, and then how, regardless of what the underlying distribution is, we can always translate into normal distribution, because normal distribution helps us do a lot of hypothesis testing, etc. So we covered that in the central limit theorem. And then next, we'll going to talk about in the next module some patterns the probability distributions create, and what are some common probability distributions, how you can use them effectively to draw some useful insights out of the data. So a lot to unpack in the next module as well. Thank you so much for staying in the course so long, if you're still here. And if whatever I have explained to you so far makes sense, I'm pretty sure that what I'm going to explain next also makes sense. And it will also be very useful as you start preparing for your interview related to statistics questions for your data science roles. Okay, so in this module, we are going to see what are probability distributions, how they are important. We are going to cover some of them. So we'll see that why does the bell curve appear everywhere? We'll go over some of the common characteristics of bell curve, which is also called normal distribution. We'll see that what are the common probability distribution patterns, especially some of the most frequently seen patterns. What are they? What are their characteristics? How they help us solve some real world business problems. And also we'll see that how does it help us predict the future. And the goal is that you, by the end of this module, are familiar with some important probability distributions, and you know what they are, and then how you can use them to solve some real world business problems. So starting with the most important probability distribution, which is called bell curve or normal distribution. This is most important distribution because in most of the natural phenomena, for example, if you're talking about human height, blood pressure, measurement errors, etc., they all follow the same distinct pattern. For example, if you survey any classroom, let's say if there are adult population in a classroom and it's a male class, let's say, and you try to measure what their height is, most likely, let's say if you were to plot the height of the people you are surveying, and let's say that we start with 4 feet height and then 7 feet, most of the people will fall within this range. And if the average male height is 5 feet 10 inches in the US, you would see that most people would have this height. And then a little bit less people would have slightly less height. Let's say if this is 5 feet 9 inches, and then slightly less people would have 5 feet 8 inches, and so on. And same phenomena occurs on the other side as well. Slightly less people would have 5 foot 11, then 5 foot 12, which is 6 feet and 1 inches, etc. So this normal distribution or bell curve is very, very common, and you will find it in pretty much most of the naturally occurring phenomena. So the question then is that why we see the same bell curve phenomena happening for most of these processes, why it's not random or chaotic distribution, why it's not zigzag like that. One explanation is that most of these naturally occurring complex phenomena, for example, blood pressure or human height, they are a result of a combination of reasons. So what we studied in central limit theorem is that if there is a sample average coming from different sources, and then you take an average of it, that usually results into bell curve. The same thing is happening, for example, for blood pressure. Blood pressure is a result of multiple things. It could be the genes, it could be the diet pattern, it could be the weight. So it is a result of multiple things which are contributing towards it. So it is sort of an average thing of it. That is why it is following the bell curve or normal distribution. And the same goes for human height. All these naturally occurring phenomena, since they are a result or a byproduct of multiple factors, that is why we are seeing them resulting into the bell curve because of the central limit theorem. So that is one explanation around it. But regardless, it is one of the most prevalent, one of the most common, and one of the most useful probability distribution, because using that, as you would see, we can use some of its characteristics to derive some very valuable business insights. Okay, so once we know that any phenomena which we are studying, for example, human height or blood pressure or whatever, once we know that it follows normal distribution or bell curve, then there are some characteristics of the bell curve which help us predict the future. And the main famous rule is 68, 95, 99.7 rule. What does it mean? That once you have your probability distribution, which is normal, let's say if this is your normal distribution, and you know that the center of this is the mean value, so this is the mean, and then if you know the standard deviation of it, so let's say this is one standard deviation towards the left, this is second standard deviation towards the left, and this is third standard deviation towards the left, and similarly one standard deviation towards the right, second, and this is third, then within this interval 68% of the results will fall. Within this interval, which is within two standard deviations, 95% of the results will fall. And similarly, within this interval of three standard deviations away, 99.7% results will fall. So this is what this famous 68, 95, 99.7% rule indicate. And why this is so important is that it helps us predict the probability of different things happening. Let's say that you have a factory and you know that the average length or the mean length of the part which you produce is 10 centimeter. And let's say if you know that the standard deviation of this is 0.1 centimeter. Then based on that, you already know what the average is. And if you know the standard deviation, which you can calculate from your prior data, then you can know from this distribution that if 10 centimeter is your average, and then this is going to be 10.1 centimeter, this is going to be 10.2 centimeter, this is going to be 10.3 centimeter on the right, and then on the left, this corresponds to 9.9 centimeter, 9.8 centimeter, and 9.7 centimeter. So this is your average, one standard deviation, two standard deviation, three standard deviation, and similarly on the towards the left. So by looking at this bell curve, you know that if 10 centimeter is your average and 0.1 centimeter is your standard deviation, then 95% of your parts will be within the range of this and this, which is 9.8 centimeter to 10.2 centimeter. Anything which is below 9.8 centimeter is faulty and you cannot use it. Then you would know that 5% of the parts are either 10.2 centimeter plus, 9.8 centimeter less. So in this case, if you are only interested in figuring out what percentage of your parts are below 9.8%, then you can just divide it by 2 because 5% represent 9.8, less than 9.8 and more than 10.2. So if you're just interested in 9.8 and less, then it's 2.5% of your parts which are less than 9.8%. So that helps you make a lot of business decisions, that is it an acceptable error number or not, or should you invest in upgrading your machines if this is the production quality of your machines. So questions like that, once you know that you have a normal distribution, are very easy to answer because of the 68, 95, and 99.7% rule. Okay, so we covered the most important and most prevalent distribution, which was normal distribution. Another one which is very common and very important is Pareto distribution. It is also called 80-20 rule. Wilfred Pareto was an Italian mathematician. He was studying the wealth patterns in Italy, and he realized that 80% of the land was owned by 20% of the people. And then he further started investigating this pattern, and he realized that this was prevalent everywhere. He documented that 80% of the peas in his garden were coming from 20% of the plants. And in data science, we also know that 80% of the bugs come from 20% of the features. We know that 80% of the revenue comes from 20% of the customers. We know that 80% of the complaints also come from 20% of the customers. So this pattern is very prevalent, but it is not, if you plot it, it doesn't look like normal distribution. So this is normal distribution, but this pattern is different because this pattern has a long tail. So it looks something like this. There are, let's say these are the 20% people, and then this is the 80%, the remaining. So these 20, they contribute, let's call them 20% few, and then these are 80%. These 20%, they contribute most towards the outcome than the remaining 80%. And in data science, if you focus on these vital few, which is this 80%, see that what are their buying patterns when they are customers, what are the feature patterns if they are resulting most amount of bugs or most amount of complaints, then just isolating them and then focusing them is a huge and immense business value in most of the cases. Okay, so another very important probability distribution, and it is one of the simplest one to start with, is Bernoulli distribution. Bernoulli distribution basically indicates when an event has just two possible outcomes, yes or no. For example, if it is a flip of a coin, then we know either it is going to be head or tail. If it is an add click, then we know that either it is click or no, yes or no, whether they clicked or whether they did not click. So anything where there are only two possible outcomes, yes or no, happening or not happening, that is called Bernoulli distribution. And it is a very simple distribution which might not be very, very relevant in its own, but it is a building block for a lot of other important distributions like binomial distribution, Poisson distribution, which we are going to cover next. And if you were to plot it, since it's like a very simple distribution, usually on x-axis you have two categories. For example, yes, and then there is no, and then you plot the probability of each of those. Let's say the probability of yes in a case of add click is, I don't know, 0.4. Then the other probability would be 0.6, because these two probabilities have to sum up to 1, which is the total space of probability. So this is called Bernoulli distribution. Again, a very simple and a very commonly occurring probability distribution. But the power of this lies is that this is a building block, more complex and more useful other probability distributions, which we are going to cover next. Okay, so now let's talk about binomial distribution. A very, very important distribution. And this is basically when we have a sequence of Bernoulli trials, something happening or not happening, then that is plotted as binomial distribution. So in this case, we can see what are the chances of k successes happening in n trials. So what are the chances of a user clicking on an ad, and when we are talking about 100 customers or 1,000 customers. So that is what is called binomial distribution. And since binomial distribution is basically a sum of Bernoulli trials, it also follows the normal distribution pattern, which means that we can use the findings like 68, 95 and 99.7% pattern. So we know that if this is the mean, then within one standard deviation, we'll have 68% of the results. And then within two standard deviation, 95% of the results, and so on. And we can use these findings to see that if the result of an A/B test is valid or is it just luck. For example, if we know that 10% of the people click on the button, and then if you launch a new button and now you're seeing 13 clicks, you can see that does it fall within this two standard deviation range or not. So this is your 95% confidence interval. If it does fall somewhere here, then it could be just by chance. But if it falls way out here, if this 13 is way out here, then you know that this cannot be by chance. And this is something related to this new change which you have made, which means that this new button which you have introduced has higher click-through rate. Instead of 10%, now it is 13%. And it cannot be happening just by chance, because we have plotted this probability distribution and we know what is the standard deviation. And if we know that this 13 is way beyond many standard deviations from the mean, that means it cannot just be happening by chance. And that actually means that this new button which we have introduced is much better than the one we were using before, with an average of 10% click-through rate. So binomial distribution is a sum of Bernoulli trials, and since it follows a normal distribution kind of pattern, we can use those characteristics to find that if an A/B test which we are conducting, or if a new change which we have introduced, is the result we are seeing just by chance, or is it actually a statistically significant result. It helps us answer that kind of questions. Another very important distribution is Poisson distribution. It is very similar to binomial distribution, but the difference is that here you are seeing how many events are occurring in a given time period. For example, you can see that how many cars are passing by a certain point in a road in an hour. So that is your time interval. You can also see that what is the average number of calls your call center is receiving. So stuff like that, where you have a given time period and you're trying to see how many events are occurring within that time period. It could be a day, it could be an hour, a month, whatever. Then that is Poisson distribution. And here the condition is that the event occurs at a constant average rate, so that there is no factor of seasonality, and you can consistently say that on average within this period of time you can expect these many results. So that is the condition for Poisson distribution. And again, similar to binomial distribution, Poisson distribution, if the mean is large enough, then it follows the same normal distribution pattern, which means you can use similar to 68%, 95%, and 99.7% pattern. The caveat here is that the Poisson distribution should actually exactly be following a normal distribution only when the mean value is large enough. But once you see that it is following this pattern, you can use this 68, 95, 99% kind of rule to realize that if the difference you are seeing is statistically significant, and you can also plan your resources accordingly. For example, if you have a call center and you know that on average you receive 30 calls per hour and you need 10 people to be able to answer these 30 calls per hour. Now the question is that how many resources do you need to be able to manage the calls 99% of the time? So in this case, you have to do this bell curve analysis to figure out that if, let's say, this is 30 and your standard deviation is, let's say, 10, then one standard deviation, 40 calls, two standard deviations, 50 calls, and then 60 is your 99.7% coverage. So anything below that is 99.7. And in this case, you would know that you need to be able to manage 60 calls per hour if you want to have 99% coverage. And that means you need 20 people instead of 10. So that even if the average is 30, if you want to be able to manage the call load 99% of the time, and since there could be surges, you need to have 20 people staff. So it helps you make that kind of business decisions, because if the mean is large enough, then basically you can use the findings of the bell curve to make some business related decisions here as well. Okay, so let's see what are some common interview questions which you can expect out of this module. A very common one is, what is the difference between binomial and Poisson? We saw that they both have some underlying similarities. For example, they both are relying on Bernoulli trials happening. We also saw that if the mean becomes large enough, this both start following the bell curve distribution patterns. But the difference for Poisson is that it is over a period of time, whereas binomial is not. Another important question is that how would you check if the data is normal? Because to be able to run that 68, 95, 99.7% rule, you need to first know if the data is almost normal or approaching normal or not, because if it is not normal, then you cannot use it. And the same logic applies when you're trying to feed the data into different algorithms. For example, if you are planning to feed the data into linear regression, you want to know that if the data is following normal distribution or not. So there are some tests which you can use. The easiest one is that you just plot, and then there is QQ plot test which you can use to see that if the data is normally distributed or not, and there are some other statistical tests for that. Another question could be that they'll give you a scenario and then they'll say, okay, what kind of probability distribution you can expect out of that. For example, the call center example which I gave, that could be a question in interview as well, that if you have a call center, you are on average expecting this many calls per hour. What do you think the probability distribution pattern is going to apply in this case? And then once you answer that, then the follow-up question could be that if the average number of calls per hour are these, and this is the standard deviation, then if you want to be able to answer 99% of the calls, what kind of staff do you need and what kind of calls per hour you can expect? And then sometimes in the interview, they can just ask, okay, if you were to explain this probability distribution to a non-technical stakeholder or executive, how would you explain it? Sometimes they say, okay, how would you explain it to a 5-year-old? Just to understand that if you have clarity on the intuition behind these probability distributions or not, or if you are just memorizing the formulas, etc. So these are some popular interview questions which are usually asked around probability distributions. Okay, so this was a relatively quick module to cover, but we covered some of the common probability distributions. We saw normal distribution, we saw Pareto distribution, Bernoulli, binomial, and Poisson distribution. We learned that what are the conditions under which we know that this is the kind of probability distribution it is, and then what are the benefits of each of the pattern and how we can use it to derive some business decisions. In the next module, we are going to cover that how we can use the power of sampling to draw some inference and business decisions about the whole population. Because in most of the settings, we cannot just get the data about the entire population, which means we have to rely on smaller samples. So how we use that effectively is what we are going to cover next. All right, well, welcome to the module 5 of this course. In this module, we are going to start with a very interesting historical story in which we'll see that how a huge poll about finding that who is going to win a US presidential election failed while a small one succeeded. We'll see that how you can use some effective techniques to sample the population and understand what are the trends which are happening throughout the population. We'll see that what are some sample biases which you can avoid by making intelligent sampling techniques. And then also we'll see that how we can make confident estimates from very small samples of the entire data set. There is a lot to cover in this module, so let's jump right in. So let's begin this module by going through an interesting story. So the year was 1936, and at that time, one of the biggest digests, literary digest, they had a poll in which they wanted to see that who is going to win the next US presidential election. And it is interesting to note that from 1916 all the way till 1936, Literary Digest had always done this poll before the US presidential election, and they were always right. So in 1936, again, repeating the same exercise, they created a poll in which they sent out the poll to 10 million people, and out of that, 2.4 million people responded back on who they are going to vote in the upcoming election. The digest clearly indicated that Alf Landon is going to win the presidential election with a landslide victory. But what happened actually is that FDR, Franklin D. Roosevelt, won the election with a majority victory. And it was interesting to note that he won in every single state. So, though the exercise of voting was very big, they sent out 10 million people with the polling card, and they sent it out by postal mail. So it was a very expensive exercise, sending 10 million people that postcard with a return envelope as well, so that they could send back what their responses are. And after spending so much money and with such a big exercise, they still failed to predict who is going to win the election. And the failure was not a subtle one, it was a big difference, because they said Alf Landon is going to win the election with a majority victory, and instead FDR had a landslide victory. So we are going to see how even such big polls can fail, and what are some reasons which are contributing towards this, so that when you are doing the sampling, you can do it more intelligently. So let's see what is sampling, what is bias sampling, and why Literary Digest was unable to predict who is going to win the election, even after spending so much money and having so much influence. So to begin understanding sampling, let's first understand population. Population is the entire population which is available, which you want to understand the trend of. In this case, in the case of Literary Digest, they wanted to understand the entire population of the United States, who are they going to vote for. And then a sample is a subset of that population, which we have access to and we have data for. And using the data we have available for the subset, we try to understand what are the patterns in the entire population. So if I were to draw it graphically, if this is your entire population, then within this we get a subset of it, which we called sample. And our goal is to get such a sample that it is a miniature version of the entire population. And the failure happens when this miniature version of the entire population is not a representative of the entire population. The mistake which Literary Digest did was that though they send out the postal mail for the polling to 10 million people, those 10 million people was not a true representative of the entire population of the US, because Literary Digest sent the samples, sent the poll surveys to their subscribers who were wealthy Americans. Even in 1936, which was a year within Great Depression, these people had cars, these people had telephones, they had membership of the country clubs. So the sample which they had, it was not a miniature version of the entire US population. It was a miniature version of the wealthy American population. And since most wealthy Americans used to vote for Republican Party back then, that is why the results of this survey was that they thought that the Republican Party is going to win. But instead, Democratic candidate FDR won the election with a landslide victory. So whenever you are doing some sampling of the population, you just have to make sure that the sample is a true representative of the entire population. How you do that, we are going to see that next. So let's see that when you are doing some sampling, how you can make sure that your sample is unbiased. So one technique is that you just purely pick simple random samples from your entire population. There's no criteria, just randomly pick some samples. This is very simple yet very effective technique to make sure that there are no biases introduced in your sampling technique, just like the Literary Digest had when they were trying to poll the people. Another interesting technique is stratified sampling, in which you try to divide your population into different segments, and then from each segment you randomly draw some samples. And that is the exact technique which George Gallup used in the same 1936 US presidential election. And he was able to correctly predict the victory of FDR with just a sample of 50,000 people. Now compare this 50,000 people with 2.4 million people, which the Literary Digest surveyed. And even with 2.4 million, their results were incorrect. And with just 50,000 people, because George Gallup did some stratified sampling where he segmented each region, and then within each region, he had people within different economic status, and then he very intelligently sampled that, he was able to identify correctly who is going to win the election. So in nutshell, a smaller, well-chosen sample beats a huge, biased sample every single time. So even though you want your sample to be as big as possible, what is even more important is that that sample is unbiased, so that the results you draw out of that are conclusive and valid. So stratified sampling is great, but what if you already have a sample, as you cannot get more, and you want to understand that how much uncertainty exists within your sample? For that, there is a recent technique which is called bootstrapping. And the core idea is that you take samples from within your sample so that you could understand the uncertainty. For example, if this is your entire population, and within that you have taken this sample. Now, you have taken this sample, it's great, but if you want to understand that how much variability within this is, that within your sample, you keep taking more samples, maybe 100 times, 1,000 times, and then you see that how much variability there exists, and then what is the confidence interval which you can build around it. Shortly, we're going to do a lab in which I'm going to write some code to demonstrate this point to you. Again, it is a very compute intensive thing which statisticians previously weren't able to do, because you have to take 10,000 samples, 15,000 samples every time, and you have to do it a lot of times and then calculate the result. But with the help of computers, we can do it pretty quickly, pretty fast, and I'm going to show you that shortly. So confidence intervals is a key concept used in hypothesis testing, and whenever we are trying to report our results to any target audience. For example, when George Gallup did the survey, he could have said that there is a 56% chance of FDR winning, because that is the pattern he had seen in the poll results he did. But what is missing from this is that how confident he is that FDR is going to get 56% of the votes. I think that is the question which is more important. Ideally, what people want out of any analysis is that what is the 95% or 99% confidence that the result of the elections are going to be in FDR's favor. And in that case, George Gallup can report that I am 99% confident, or I'm 95% confident that FDR is going to get votes somewhere between 54% to 58%. So that kind of result is much more useful than just getting a number, because if we do not know what is the level of uncertainty in the result which we are reporting, then the result is essentially useless. So the meaning of 95% confidence interval is that we are 95% confident that the true value is within our reported range. In this case, 54%, 58%, for example. And logically, if we want to be more confident, for example, if we want to go from 95 to 99% confidence, then this range would increase. For example, it can go from 50% to 72%. I'm just making up some numbers here. But the core idea is that whenever you are reporting the results, you have to give some confidence intervals around it so that people can see that what is the level of variability you have in your data and how much they can trust these reported results. So the key question then becomes is that when you are doing the sampling and you are selecting the samples, how much data is enough? Because the thing is that if you take too little data, then that's of course very easy to get because you just have to survey very few people, but it misses the real effects. The experiments you're doing would be underpowered. On the other hand, if you were to go for gathering too much data, then you can potentially waste a lot of time and money, and that will just be inefficient. So we have to come up with some formulas to come up with what is the right number of samples we need. The term which is used for this is power analysis. And there are a lot of online calculators which you can use. There are mathematical equations for it, which I won't go into it. But at a high level, I just want to illustrate that the sample size is a function of three things mainly. It is a function of effect size, it is a function of variance, and then confidence you want to have in your results. So let's start with effect size. Effect size basically means that how much difference is sort of acceptable for you to be counted as good enough. For example, you have a website on which you have add to cart button, which is blue. And currently you are seeing 1% people clicking on that button. Now, if you change the color of that button and make some other changes, so now that is the change you have made. Now you want to know how much increase in the click-through rate happens. Now, if the click-through rate previously was, let's say 10%, and now let's talk about two scenarios. One in which you are okay with even 11% click-through rate, which is just an increase of 1%, then it is a very small effect size. Whereas the other option is that you think that this new button is very, very different and going to lead to massive results, and you are expecting 100% click-through rate now. Now, if you want to see the difference from 10% to 100%, of course, this is a very big difference. And with a very small sample size, you'll be able to notice that difference. Whereas if you want to see even 11% difference, then that's a very small, very hard to notice difference. And especially, it is very difficult to ascertain that 10 to 11% difference is just by chance, or there is something statistically different about your new approach. So of course, for that, you need a lot more data. So that is about effect size. The next is variance. What is the variance in your current data? Again, if you have 10% click-through rate now, what is the variance in it? Is it ranging from 4% to 14%? Or is it 0% to let's say 50%? So the more variance there is in your data, the more samples you need to be able to draw statistically significant results. And the last one is confidence. How much confidence you need to have in your conclusion. As we saw in the case of normal distribution, if you want to have, let's say, 68% confidence in your interval, then you do not need a lot of data. Whereas if you need 95% confidence, then you need more data. And if you want 99% confidence, then you need even more samples for that. The reality is that most people, when they are doing the calculation, they tend to think that they need less samples than they actually need. That is why most of the experiments we see happening in the industry are underpowered. So generally, when in doubt, it's better to go for slightly more samples instead of less samples, because more samples might require more time and effort to acquire them, but at least the experiments, when you run them, you'll have statistically significant and well-powered experiments. Okay, so now quickly going over some of the popular interview questions related to this section. There is a very popular interview question about Literary Digest poll. Why it failed? What do you think are the reasons? People want to know that if you have good grasp of over how do you do unbiased sampling. A related question to that is that you have a customer base to survey. and you want to sample responses from them. How would you do the sample? If you were to do random samplings, what are the pros and cons of that? If you were to do stratified sampling, how would you go about that? So there are some questions around that. Then confidence interval, again, a big one. People want to, first of all, understand that if you have a clear understanding of what does confidence interval mean, what is the significance of it, what is the importance of it, why do we usually need it, what are the factors which impact the confidence interval, and especially as we have a sample size which is growing bigger or smaller, then how does it impact confidence interval? Another thing which we have not covered yet, which we are going to cover in the machine learning masterclass, is there is a thing called prediction interval. And that is, of course, different from confidence interval. So having an understanding of what is prediction interval, what is confidence interval, how they two are different, these are some very popular interview questions related to statistics. So now let's go to some hands-on coding exercise where we are going to see that how we do bootstrapping and how that is a very powerful technique to understand the patterns within the entire population, and we can see that how we can find the variability within our sample using that modern technique. Okay, so in this lab, we wanted to see that how we can use bootstrapping to find the variability and the confidence within our sample. And for this, I'm going to use this IMDb movie dataset. It has 10,000 plus movies worldwide, and it has a couple of things about each movie, but mainly the thing I'm interested in is score. And it is between 0 and 100, and I want to see that for each movie, what is the score and what is the average score of that, and how we can basically take a very small sample to understand what's going on and what is the expected average. So this is the notebook. All of this code is generated by AI. Within Google Colab, you can basically use generate to write some function. You can just explain in natural language what you want it to do. So the setup is I'm just importing certain libraries which I need. Then I want to see that what is the actual mean value, the average value of the score for all these 10,000 plus movies. So there are 10,000 plus movies here. And then I have calculated the true population mean here. I'm not printing it here, but I've calculated it so that later I can see that was I able to predict this mean value, and was it within the required confidence interval or not. So the next step is that I have created a small sample, just 100 movies. We have 10,000 plus actual movie ratings here. I'm just taking a sample of 100. It is less than 1% sample here. And then for that, I've calculated the mean. The sample mean for our case is 61.3. And then I've calculated the standard deviation, etc. Standard deviation is 15. And this is what the data distribution looks like for the 100 movies. Now, as a next step, I'm trying to do the bootstrapping. In the bootstrapping, I'm trying to get 10,000 samples each time, and I'm going to run it a bunch of times. And every time I'm going to take some samples, and then I'm going to calculate the mean value of it, and I'm going to do it 10,000 times. So this is how the code runs. Every 2,000 iterations I'm printing. So I'm saying that 10,000 bootstrap resamples happen, 2,000 bootstrap resamples happen, 4,000, 6,000 onwards. And then by then I've generated 10,000 bootstrap sample means. And then based on that, I'm calculating the confidence interval. And as you can see, the lower bound for the 95% confidence interval is 58.289. And then the upper bound is 54.13. And there is a margin of this error here. Now, if our true score is within this range of 58.28 and 64.13, then that would mean that most likely 95% chance this range is correct. So let's see what our actual range is. So as we run this, the actual range is 63.4. And it is within our confidence interval, and this is success here. So the big insights are that with just 100 movies, less than 1% of the data, we were able to remarkably accurately estimate what the actual mean value is. And that is with the bootstrap magic. Now, let's say that if I want to take a different sample, let's see what happens. Let me change the random state here. Let's say if I were to do it 49 and rerun the code. Now, this time our sample value is 64.7. And then if I were to redo this, the confidence intervals again would be different. But most likely, our actual value of 63.8 would still fall within this. And that is true. So again, this is just a simple coding exercise to demonstrate to you the power and the usefulness of the bootstrapping algorithm. So we covered a lot of things in this module. Let's quickly recap. We learned that how a good small sample beats a huge biased one. And we saw it in the case of George Gallup versus Literary Digest polls of 1936 US presidential elections. And then we saw that how you can sample smartly by taking random and stratified sampling. We also saw that how we can express our uncertainty in our results by using confidence intervals. The next logical step for this is that how can we formally do some hypothesis testing, and that is going to be the subject of the next module. Okay, so welcome to the module 6 of this course. Now we are going to start talking about some very interesting concept, which is mainly hypothesis testing. And we will start with a famous story behind lady testing tea, what that experiment was, and that how that opened up door for some important statistical concepts like hypothesis testing, p-value, and significance testing. And we'll see that how A/B tests and other common statistical tests work, and then how you can use these tests to make some data-driven decisions. And A/B testing and these modern statistical testing, these are the backbone of modern-day businesses. Modern-day businesses, they run A/B testing on pretty much every single feature they launch, especially when we're talking about digital businesses. When I was at Meta, we used to run hundreds of A/B testing for different things, trying different variations of even small, slight things. Same is true for Cisco. And a very popular data scientist, Roni Kohavi, shared a very insightful example of a data scientist at Bing who was trying A/B testing on different things. And he tested this variation where against the title of each search result in Bing, they added some explainer detail, though it was a very small, subtle thing. And the moment they launched this test, within hours, the revenue increased so much that they started getting alerts that there must be something wrong with the system. This is the power of A/B testing, and that is why companies like Google, Facebook, Amazon, they are running hundreds, sometimes thousands of tests every single day to optimize every small minor detail within their website, within the user experience, so that they could be the best website they can. And that leads to increase in revenue, increase in customers, and increase in growth for the product. So in this module, we are going to unpack that. But before we get to that, let's start with an interesting story for this module, which will help you make sense of the rest of the things. So let's start with the main story for this module. The story is of a lady tasting tea. The story is based off a tea party which happened at Cambridge, and in Cambridge in the year 1926. The story goes that there was a lady at this, her name was Muriel Bristow, and she claimed that whenever a cup of tea is presented, she could tell that if tea was poured into the cup before the milk, or milk was poured into the cup before the tea. Though for an ordinary person, it's very difficult to tell that which got poured into the cup before, because the end product is still the same. But she claimed that she can tell. And a lot of people were sort of laughing at the claim, but lucky for us, there was a statistician named R.A. Fisher who was also present in that tea party. So he said that he wanted to test the claim of the lady. So the question became that, of course, anyone can take a guess at if the tea was poured into the cup before the milk or not. There's a 50-50 chance of guessing it correctly. So the question is that how many cups of tea the lady has to correctly predict so that we could prove the claim that she has this insight that she can tell if the tea was poured into the cup before the milk or not. And that discussion and that brainstorming led to the invention of the modern hypothesis testing framework, which we are currently using in so many places. And the use cases for that test is prevalent everywhere. If we are testing website, we want to see if we change the button color, does it have statistically significant improvement in the results? If we are testing the drugs, we want to know that if the new drug is statistically better than the previous drug or not. And so on and so forth. There are so many use cases for this hypothesis testing framework, which R.A. Fisher discovered as a result of this tea party discussion. Okay, so before we go deep into how hypothesis testing work, let's look at some of the terminology we use. So we always state the hypothesis first, and we state it in two ways. First, there is a null hypothesis. That is always the skeptical view. It is skeptical view because the null hypothesis mostly state that the difference we are seeing is just purely because of luck, and in reality there is no meaningful difference in the result. So in the case of the lady testing the tea, the null hypothesis would be that she is just guessing. The alternative to that is alternative hypothesis. And that is a claim that the difference is actually statistically significant. In the case of the tea party, she can actually tell the difference. So null hypothesis is always the skeptical view. We do not think there is any change. Any change we are seeing is because of pure coincidence and luck. And the alternative hypothesis is the opposite of null hypothesis, in which we say that the results are actually different. And the goal here is that we want to find enough evidence so that we can reject the null hypothesis. Again, the key difference here is that we never prove the alternative hypothesis. It's always that we start with the position of skepticism, that we do not believe there are any differences in the two things. And then we try to find enough evidence to prove that the null hypothesis is incorrect, and then we can reject it, and that helps us believe in the alternative hypothesis. So in the case of the tea party, logic is that we assume she's guessing and then see how surprising our result is if she is guessing. If it is very surprising, then we can reject the null hypothesis and then embrace the alternative hypothesis. Okay, so that brings us to the question, what is a p-value? It is a very important term which gets asked in the interview questions, and you'll see a mention of it a hell lot of time in pretty much every statistical book. If you run any machine learning statistical algorithm, you would see this value coming up. So very, very important concept. So what is it? It basically is the probability of seeing the results or more extreme results if the null hypothesis were true. So in the case of the lady testing the tea, if the null hypothesis is true, again, the null hypothesis is that she cannot tell the difference between two cups if the tea was poured before the milk or milk was poured before the tea. If that null hypothesis was true, then what is the probability of seeing the results which we are seeing, or more extreme results? So let's say if we were to give that lady 1 cup, let's say if we just give her 1 cup, and we ask her to tell if the tea was poured in the cup before the milk or not, and let's say if she guessed it correctly, then if the null hypothesis was true, then what is the probability of us seeing that result? It is 0.5, right? It is 50%. Now, let's say if we were to give 2 cups of tea to her and then ask her to predict. Or even, let me make it more complicated. Let's say if we gave her 8 cups of tea and ask her to predict which cups had poured tea before. And let's say if she is able to correctly tell that these are the cups which had the tea poured in before. Now we have to see that what are the total number of possible combinations which could have happened in this case. So this is a problem of combination. So this basically becomes 8 choose 4, and the answer for that is 70. So there are 70 possible combinations of this, and if she picked the correct one, then the odds of randomly happening that, if the null hypothesis was true, would be 1 in 70, which is very, very rare. And that brings us the p-value of 0.014. That what is the probability of us seeing this result, that this lady is able to correctly predict it, given there were 70 options, given that null hypothesis was true. And let's say if we were to make this test even harder, and there are 10 cups to choose from, let me add 2 more cups, and then 5 of them have tea first and 5 of them had milk first. Now it's a problem of 10 choose 5, and there are 252 combinations to choose from. And if she still gets it correct, then the odds of us seeing this result, if the null hypothesis is correct, would be 1 in 252, and the p-value would become even smaller. So in nutshell, that what p-value means is that it is the probability of us seeing the result which we are seeing, or even more extreme results. Given the condition, if the null hypothesis were true, and if the p-value is smaller, then our result is surprising and evidence is against the null hypothesis, which is also represented at age of 0. And if the p-value is large, our result is not surprising, and there is not enough evidence that we can reject the null hypothesis. Okay, so we talked about the p-value, and we talked about that we need to have enough evidence that we can reject the null hypothesis, and only in that case we accept the alternative hypothesis. But the key thing there is that we need to have enough evidence to be able to reject the null hypothesis. Just because we do not have enough evidence to reject the null hypothesis does not mean that the null hypothesis is actually true. So in the case of that tea testing, let's say if that lady actually has some magical power and she can actually tell the difference if the tea was poured in the cup before the milk or not. And we just give that lady 1 cup of tea and ask her to judge that. Now, if she correctly tells if the milk was poured in the cup before the tea or not, then what is the probability of us seeing the result if the null hypothesis is true? It is 0.5 or 50%, which is 1 in 2. Now, this is not enough p-value for us to reject the null hypothesis. But just because we are not rejecting the null hypothesis does not mean that the null hypothesis is correct. Because the null hypothesis says the lady cannot tell the difference, but in this case, actually the lady can tell the difference. It's just that we have given her only 1 cup to test. So that brings us to the power of the test. The test has to be powered enough. There should be enough samples that we can detect the real effect without problem. And the statistical power of the test indicates that what is the probability of correctly rejecting a false null hypothesis. We want to have enough samples, that we want enough power in the experiment that we can avoid false negatives and we can avoid type 2 error. Now, what is false negative and what is type 2 error? Let me expand on that a little bit. So usually when you are predicting something which is yes or no or has binary outcome, then there are some real values and then there are some predicted values. Generally, it is shown into this matrix, which is called confusion matrix. So let's say here we say if it is predicted yes, predicted no, and then actual yes and actual no. Now, if the actual value was yes, and then you predicted yes, then we call it true positive. Similarly, if the actual value was no, and the predicted value is also no, then we call it true negative. True means that the prediction was correct, and the positive means that the value was positive. And similarly, true means the prediction was true, and negative means the value was negative. Okay, similarly, if the actual was yes and you predicted no, then that becomes false negative, because it was a wrong prediction and you predicted it as a negative. And if the actual was no and you predicted yes, then that's false because the prediction is wrong, and that is positive because you wrongly predicted it as positive. So the false positive is this area when the null hypothesis was actually true and you incorrectly rejected it. Whereas type 2 error is this one when the null hypothesis was actually false, but you were unable to reject it. In most of our hypothesis testing, our main goal remains that we don't want to commit type 2 error, and we want our experiment to be powered enough that we can avoid false negatives. Now, there are three factors which impact the power of the test. One is sample size. The more samples we have, the more power the test is. That is sometimes the easiest lever which you can move. The second one is effect size. Let's say if you have two buttons, and this is button 1 and this is button 2. If the difference between these two buttons is 100%, if this has a click-through rate of 10% and this one has 20%, then that is much easier difference to gauge, and that would improve the power of the test. Instead, on the other hand, if let's say the difference is 11%, now this is a very small effect size, very small difference to measure. And of course, in that case, the power of the test would be lesser. And then there is significance level, that how much significance you need in the test. Generally, you need 95% significance level. But if you need more, for example, 98% or 99%, then you need a test which is even more powered. And if you recall, this is similar to the sample size calculation which we did in the last module. Okay, so now let's look at how the modern A/B testing is done in the websites, in any user experience portal, and in a lot of other changes which businesses are making on a day-to-day basis. So as the name implies, there are two versions. There is A and then there is B, and then you test both. So let's say if you want to change the color of a button, then to some users, you would show button A, let's say if it's a blue button, and then for other users, you would show a B version of it, which is, let's say, a red button. And then the task of the hypothesis test is to see that if the difference between the two is statistically significant or not. And this is very similar to the Fisher's t-test, because again, here you are looking at two things, and then you're trying to see that if the difference you are seeing, if there was no underlying difference, that is your null hypothesis, then is the difference which you are seeing can happen because of chance or not? And that becomes your alternative hypothesis. And then you collect enough data to see that if the null hypothesis were true, then what are the chances of us seeing that difference? And if the p-value is small enough, then they reject null hypothesis and embrace the alternate hypothesis. And if the p-value is big enough, then that does not allow us to reject the null hypothesis. And that means we have to maybe get more data or try different versions. So let's now talk about some common hypothesis tests. So t-test is the most common one, and it helps us test the mean value of two groups. Let's say if you are trying to measure the average adult male's height in US, let's say if this is US, and then you're also trying to do it in Africa. And The mean value here, for example, is 5 feet and 10 inches. And here, let's say if it is 5 inches and 5 feet and 6 inches. Then the question is that if the null hypothesis is true, which is always the point of skepticism, that there is no difference in both, then what is the chance of us seeing this difference in the mean of 0.4 inches? Now, there are mathematical formulas and online tools in which you can just feed the data and get the results. But just to convey the point through intuition, basically what we do is we try to understand that how much variance is it in both these distributions. Let's say that when we plot this US data, and we get a plot like this. Let's say if it is like this, the average value is 5 feet 10 inches, and then we plot the distribution of African male heights. And let's say if that is here with an average of 5, actually it should be on the other side. Let's say if it is 6 feet and 1 inches, 6 feet 1 inches. Now we would see that if this is the distribution, then of course these two are very far apart, because our chance of seeing this as average would not happen if this distribution is true. But on the other hand, let's say if we find a distribution which looks like this is 5'10" for males in the US, and for Africa, let's say if it is this, where this is 6 feet 1 inches, then we can see that that is this result of us seeing the average value of 6 feet 1 inches. It can happen because of chance. In this case, it is difficult to happen by chance. So that is the kind of analysis we are trying to do when we are running the t-test. ANOVA is similar. It is analysis of variance. We do it when we have more than 2 means to compare. So let's say if we are trying to see if the height within US and Africa and some other country, let's say Asia, they are different, then one option is that we do a lot of t-tests. We first compare US against Africa, and then Africa against Asia, and then Asia against US. We can do all those tests. But the problem with that is that when we have a significance level of 95%, and we are 95% confident in our results, there is still 5% chance of error, which means 1 in 20 results could be false. And when we are trying so many combinations, our chance of bumping into those incorrect results are high. So that's why ANOVA does a little clever calculation, but essentially the same concept when we have more than 2 means to compare. Now, talking about chi-squared, it is also a very interesting hypothesis test when we have some group means. Again, a high-level intuition for this is that, let's say, if we are trying to see that there are 3 headlines which we are trying to test. Let's say there is headline 1, headline 2, and headline 3. And then we are seeing the result of some users clicking on it and some users not clicking on it. Of course, a lot more users will not click. And let's say if the data we have is 14, 8, 12, and the users which did not click is 986, 992, and 988. Now, the question we want to see is that if the null hypothesis is true, which means there is no difference in the click-through rate of these headlines, then what are our chances of seeing this distribution? So at a high level, what we do is that we'll say, okay, if the null hypothesis is true, then their underlying distribution should be something which is the average of these. So that will become 11.3 for all of these. This would be 988. If the null hypothesis is true, this is what we should see. And then we basically find the difference between these two, 14 versus 11.3, this versus this. And if this difference is bigger, then that means that null hypothesis is probably not correct, because we are seeing a lot of variance in these ratios. But if this difference is smaller, then we can say that maybe they're all generated from the same underlying distribution, and the little bit differences which we are seeing are just because of luck. So basically, all these tests, they boil down to a simple idea. We want to see that what is the ratio between signal and noise? And noise is pure, random, coincidence, chance. The variation because of chance versus variation because if there are actually underlying differences. That is what we are trying to test through all these tests. Now, one drawback of using A/B testing, though A/B testings are great, is that when we are sending 50% of our traffic to something which could be not very optimal, we are wasting a lot of resources. And that actually becomes true when the experiments you are running are very expensive. Let's say if you have a website where you are selling some stuff and then you make some change and you want to test it, you send 50% of your traffic to page A, 50% of traffic to page B. And let's say page B for some reason is not very optimized. And because of that, a lot of people are not buying your product because you're testing, then that is a loss of revenue. And that led to this idea of multi-arm bandit. When we look at the origin story of it, it was actually invented in World War II because at that time, US wanted to fully optimize their resources. They did not have enough time and enough resources that they can properly A/B test a lot of combinations of their devices, of their war machines, etc. So in that context, a conclusion that they arrived on the solution of multi-arm bandit. The basic idea is that as you start the test, let's say even if you start with 50-50, the moment you start building a little bit confidence that solution A is better than B, then you divert more traffic to A and less traffic to B. And then as you develop more confidence, you keep diverting your traffic or other resources to the solution which is working. So you basically dynamically shift your traffic to the winning version during the test. You don't have to wait till the end of it. You can do that during the test. And it can work in A, B, C or multiple variations as well. Let's say that you want to try 5 variations. There is A, B, C, D, and E variations. And you send some traffic to these 5 pages. And let's say version A is slightly better than the rest. Then you are now sending 80% of your traffic to version A and only 20% to the remaining ones to see that maybe they are a little better. And as you get more confidence into the results, wherever you think is the winning page, you send more traffic to it. So this is a very crucial and a very intelligent technique to maximize the results while you are still testing that which combination is better. Okay, so now coming to what kind of interview questions you can expect out of this module. So probably the most important one is p-value. You should have a very clear understanding of what is p-value, and you should be able to communicate it to business stakeholders in non-technical terms. Another key thing we mentioned here is type 1 and type 2 error. What does it mean? And also, what is false positive? What is false negative? A related concept which we'll cover in our machine learning series is what is precision and recall, because that is also dependent on false positive, false negative, all of that. When would you measure p-test versus chi-square versus ANOVA? All of these are important concepts. Well, another test which I didn't cover is f-test. You should look into that as well. And then what is the power of the test? Why it is important? What are the factors which contribute towards that? All of these are some very important interview questions. And I hope that by going through this module's content, you now have enough intuition that you can answer most of these questions intelligently. Okay, so coming towards the end of this module, let's recap what we covered. We learned that what is the formal logic of hypothesis testing. In our previous modules, we covered what are different probability distributions, why is probability important, how do we sample our population effectively. And we were sort of coming towards building enough knowledge that we can understand hypothesis testing, which was this module. So we went over the formal logic of hypothesis testing. We went through what was the story which led to the invention of hypothesis testing. We understood what is p-value, what are different kind of errors, type 1, type 2 error, what is the power of a statistical test. We look at what are different common statistical tests available, t-test, f-test, ANOVA, chi-square test. And the idea was that using these tests that we can establish a relationship that if some intervention is actually causing improvement or changes in the outcome. But that is not all, because that part of identifying the cause is a whole science in itself, which is the science of causal inference. It is a very interesting module and a very practically useful thing to learn, which we are going to unpack in the next module. Welcome to the 7th module of this course, and it is about causal inference, which is one of my favorite topics. I spent a couple of years trying to learn causal inference, some advanced techniques in it. And if you want to go a little beyond what I'm going to cover, a very interesting read is from one of my favorite authors, Judah Pearl. There is a book of why. And as the title suggests, science of understanding why something happens. And the reason I think this is very, very powerful and very useful is that once you understand why something is happening, then you can basically rectify it. You can improve its chances of either happening more or happening less. For example, if you are seeing that a lot of customers are churning, then if you could figure out why they are churning, then you can maybe prevent a lot of churns. And the same logic applies to a lot of other cases. So very interesting field of statistics, and I'm going to briefly cover that in this module. So let's see what we're going to cover. So in our previous module, we saw that how we can run hypothesis testing, and then we can see that if two things are similar or not, if anything is happening by chance or not. There is an important warning I want to give here, that even perfect statistical tests can give very wrong results with very bad consequences. We'll go over some examples. We'll go over Berkeley's paradox of admissions. We'll go and see that medicine's deadly reversal, how we thought that one treatment can actually cure and prevent a lot of heart disease, whereas it was actually causing it. And the initial results were also based on data. Go look at causal diagrams and then natural experiments and different paradox deduction so that you do not make the same mistakes which previously happened in some of the examples we're going to go over. And then we'll see that how you can go through sometimes even deceptive data to find the true causes of what is causing what. So basically understanding why something is happening. So very interesting subject, and we have a lot to unpack here. So let's jump right in. Start with the Berkeley paradox. This is about UC Berkeley in California. And in 1973, there was a lot of allegation against the university's admission office because the admission rate for men was 44%, whereas that of women was 35%. So there was an allegation that the admission office is prioritizing men and giving more admissions to men, and less women are admitted. There were a lot of lawyers who were rolling up the sleeves to file some lawsuits, and this was up in the news, causing a lot of bad publicity for university's brand name. But when they closely looked at the data, department by department, they realized that actually women had higher admission rate for pretty much every department. So how is that possible? That overall, women have fewer or lesser admission rate, whereas when we look at department by department, mostly women have higher admission rates. And it's only in some departments when they have lesser admission rate than men, The difference was very subtle. So how is that even possible? Now, to understand that, let's look at data. So this is the data. This is aggregated numbers, and this is at subject by department. They have not given the actual department names. Instead, we know department A, B, C, D, E, and F. So let's look at the aggregate data. So there were about 12,000 plus total applicants. So it was a decent enough sample size, and overall admission rate is 41%. But when we look at men's admission rate, it is 44%, whereas for women it's 35%. So of course, women were getting less admissions as compared to men. So that is the story which the whole or aggregated data is telling us. But now let's look a little more closely. Now, when we look at department by department, we see that for most of the departments, the admission rate for women is higher. For example, department A, 62% for men, 82% for women. So for department A, women had higher admission rate. Same for department B, same for department D, same for department F. It was only department C and E in which their admission rate was lower than that of men. And even here, the difference is subtle, 34%, 37%, 24%, 28%. So how is it possible that when we look at department by department level, we are seeing that women are admitted even more than men, whereas when we look holistically and when we look at the aggregated data, we are seeing a totally different picture. This is a very common phenomenon, and it is known as Simpson's paradox. And you'll see many examples of it. The reason why you are seeing this discrepancy is that women are applying for departments where the admission is tough to get. So when you look at the overall acceptance rate, you would see that for this department A, the admission rate is very high, 64%. Same for department B, 63%. And here, if you look at men applicants, there are 825 applicants as for men as compared to 108 women. For department B, 560 men as compared to just 25 women. When we look at lower acceptance rate departments, we see that more women are applying, sometimes even more than men. For example, here, department C, a lot more women than men. And because women are applying more towards competitive departments, that's why the overall admission rate for them is lower. But when we look at department by department, we see the clear picture that it's not an issue of gender discrimination. It's just an issue of looking at the data in a wrong way. Another interesting example of Simpson's paradox is that, let's say if you have two hospitals, one is some very advanced cancer care hospital where advanced cancer patients go. And then there is another hospital which treats cancer as well as some other diseases as well. Now, if you look at the survival rate holistically, you would see that the survival rate of the advanced cancer hospital would be much lower as compared to the other general hospital. Whereas if you look at department by department or the kind of patient which is going on in both departments, in both hospitals, you would see that per department basis or per treatment kind basis, the advanced cancer care hospital would have better survival rate. But overall, it has a lower survival rate because more severe patients are going to the advanced cancer care hospital. So this is called Simpson's paradox. It is very common, very prevalent, and very, very easy to ignore. So it's best to understand it as a data scientist and then realize that when it is happening. Later in the module, we are going to cover a lab related to Simpson's paradox as well, so that you could see how it is happening in practice and how easy it is to get fooled by the data which is aggregated. Now, let's talk about another very popular data blunder we as statisticians made. So, for decades, there was this hormonal therapy treatment, commonly known as HRT, which was recommended to post-menopausal women because it was known that it leads to 35 to 50% less heart diseases in women. So it's not that it had a mild impact on fewer heart disease. This was a big impact on fewer heart diseases. And that is why for decades, in 1980s, 1990s, it was very, very common for doctors to recommend this treatment, this therapy, more post-menopausal women so that they could have fewer heart disease. But then in 2002, there was a randomized trial happening, and then they had to stop the trial midway. Why? Because of this hormonal therapy. And what they discovered is that HRT increased heart disease by 29%. So previously it was assumed that it decreases it by 35 to 50%, whereas now they discovered that it increases it by 29%. So totally opposite conclusions. So why did they previously concluded that it is helping prevent heart disease? Because the women which were choosing or opting for HRT, they were healthier and wealthier women. These were the women which have access to more money, and they were more health conscious. And because of that, they have access to better healthcare. So these women naturally had fewer heart diseases as compared to the other women who were not opting for HRT. And this was a very mind-boggling insight, because this reversal affected millions of women, and it totally changed how we view observational studies in the healthcare. So now, as we have looked at some of the big mistakes we can make when we are looking at the data in a wrong way, now let's figure out some ways in which we can prevent these data disasters. And these are some terms I want you to get familiar with. But before that, there are two other things you should be familiar with. One is a DAG, and then the other is controlling a variable. So what does DAG means? DAG stands for Directed Acyclical Graph. And this is the graph you should be making when you're trying to understand the relationship between different variables. And then controlling basically means that whenever we are trying to understand the impact of one variable on the other, we try to control for other things. So you need to know what kind of variables you should be controlling and what are the kind of variables you should not be controlling, so that you could draw some good results. And controlling here means that we say that if this remains constant, if this thing does not change, then what is the impact of this on that? For example, if you're trying to understand that what is the impact of IQ on earning, then we have to control for certain things. Like, okay, if we were to control for the level of education, and if we were to control for the wealth of the parents, then what is the impact of IQ on income if we have these things as constant? So this is what controlling means. Now let's look at some of these variables and how do they influence each other. So the first one is confounder. What is a confounder? Let's take an example of ice cream sale and shark attacks. So in most countries, if you were to plot shark attacks and ice cream sales, you would see a very direct correlation between both of these, because in summer, both of them go up, and then in winters, both of them go down, because there is one confounding variable which is impacting both of these. So there is temperature, which is impacting both ice cream sales as well as the shark attacks, because in summer more people go to the beaches and more shark attacks happening. So if one variable is impacting, influencing two or more variables, that is called confounder. And confounder is something which you should control for, because otherwise you would draw a wrong conclusion that maybe more ice cream sales are leading to or causing more shark attacks, which is, of course, a wrong conclusion. So you have to figure out what are the confounders. In this case, it is temperature. So then you should control for temperature and then see if there is a relationship between these two or not. The other thing is mediator. Mediator is something which impacts one thing and then that impacts outcome. For example, exercise impacts weight loss, and then weight loss impacts health. So in this case, weight loss is the mediator, and we should never control for the mediator when we're trying to understand the impact of exercise on health, because if we keep the weight loss as constant, then we might wrongly conclude that exercise has no impact on health. So anything which comes in between this chain is called mediator. The next one is collider. Collider is when both X and Y impact the outcome. For example, in the NBA success, we see that height impacts it as well as the talent. So you need to have talent and or good height to be able to have successful career in NBA. And so in this case, NBA success is the collider because it is colliding both height and talent. And you should not be controlling for the colliders as well, because in that case also you would draw some wrong conclusions. So now let's talk about some scenarios when you cannot do randomization. Remember that whenever we are trying to run some trial, our sort of the best practice is that we randomly sample two different populations and then we try to see what's going on in there. So what if we cannot get a random sample, or we cannot assign a random treatment? And there are a lot of cases for that. For example, if we are trying to see that what is the impact of smoking, then we cannot ask people to smoke. Similarly, if we are trying to see what is the impact of poverty, we cannot make people poor. And there are a lot of other cases. If there is some, we want to see what is the impact of disaster, what is the impact of going to the jail. We cannot send people to the jail. We cannot sort of induce any kind of disaster on people to see that what is the impact of certain treatment. So in that case, what can we do? Well, we do have a couple of approaches. One is the approach of natural experiments. Sometimes naturally the same population get two different kind of treatment naturally. One very good and popular example is that of John Snow. When, if you remember our module 1, when he was trying to understand what is causing cholera, and he was trying to prove that it is caused by bad water rather than a bad smell. The one thing which went good for him is that at that time, in I think it was mid 1800s, London was getting water from different water companies. So let's say this area is covered by water company A, this area is covered by water company B, and so on. So when one of these water source was contaminated, it was a natural experiment because John Snow was able to see whoever is drinking from this water source is getting cholera disease. Others are not. So by looking at these two groups, which were naturally different, he was able to ascertain that the disease is caused by contaminated water. The other option is regression discontinuity design. So let's say if you want to see that people who get into Harvard actually earn a lot more or a lot less or maybe not more than the other people who do not get into Harvard. Now, there are a lot of other variables which are impacting on people who go to the Harvard because it is an expensive university. So you need to have some sort of good financial backing. You need to have a very good IQ. You need to be very good in academic studies, which means you also are very hardworking. You should have access to bigger universities, which means that you're also raised in some sort of educated family. So there are a lot of other confounding factors which can influence both your earning potential later in life as well as your chances of getting into Harvard. So if you want to see if getting into Harvard actually changes your financial prospects later in life, then one option is that you do this study of regression discontinuity. And what it does is that, let's say, if the criteria for admission in Harvard is some standardized test, let's say it is SAT, and let's say if we see that you need to have a score of 1400 in SAT to get admitted into Harvard, then what we do is that Regression discontinuity basically means is that you find out people who are slightly below 1400. So these are the people who were not able to get admission into Harvard because their score was less than the admission cutoff. In this example scenario, let's say it is 1400 SAT score. And then you also look at people who are slightly higher than this threshold. And then you compare the financial prospects of both of these later in life. Because technically, someone who got a score of, let's say, 1388 and someone who got a score of 1402, there is not much difference in them when it comes to how good they are at studies, etc. So you take these two groups and then you try to see that how different they are later in life. And then that would give you a good idea that if getting into Harvard, which is this group, had statistically significant differences as compared to this other group, which did not get into Harvard but had similar scores. So that is the regression discontinuity design. The other one is difference in differences. So that basically means that in different groups, if some change was introduced, then how different were the outcomes. An example is that if you know the geography of the US, this is the state of New Jersey, let's say, and then this is Pennsylvania. Two adjacent states, very similar climate, everything very similar. And in 1992, New Jersey significantly increased their minimum wage, and Pennsylvania did not. So this is difference in two different states. And then you can see that what is the impact of minimum wage increase by comparing what happened in New Jersey versus what happened in Pennsylvania, since these two had similar population and then one got the change and other one did not get. So that was difference in differences. And then there is instrument variable. Sometimes you cannot directly measure the impact of one variable on the other. So in that case, you find an instrument variable, which is basically a proxy variable, to see that if it has an impact or not. Now, the proxy variable, if it impacts both, then that's not a good instrument variable. An example is that, let's say, if you are trying to see that if having more police force has an impact on the crime in the area. Now, that is a difficult problem to solve, because generally, if crime increases, then it's possible that the city would hire more police. And in that case, you might wrongly draw the conclusion that having more police actually leads to more crime, which is clearly not the case. So we cannot directly measure the presence of police force on the crime rate. So the proxy which we can take here is, for example, the hiring of firefighters. Now, in that case, the hiring of police officers, because they are sort of same cadre, cities which do have a lot of priority for safety, they hire for both categories, both for police as well as firefighters. So in that case, that instrument variable does impact X in this case, which is the hiring of police officers, but it does not have impact on Y, because hiring more or less firefighters does not impact the crime in the city. So in that case, you can take the hiring of firefighters as the instrument variable, as the proxy variable, to measure that if having more firefighters hired has any impact on the crime in the area, then you can draw the conclusion that the other variable which you did not measure, which is the hiring of police officers, also have an impact, positive or negative, on the crime in the area. So this is not the complete list of some techniques which we can use to draw some causal inference. And all of these techniques have their own limitations. None of them is the silver bullet which can help us solve all the problems. But these are the best shots we have. And sometimes you have to use multiple of these to draw some conclusions which are more trustworthy, rather than blindly following any one of these. Unfortunate truth is that a big portion of published research is actually based off findings which are not correct. And the main reason for that is p-hacking. P-hacking basically means that when we are talking about 95% confidence interval, which is typically the case, that means that there is a 5% chance that what the results you are suggesting are incorrect. And when we have to make a lot of choices, what kind of variables to pick, what kind of test to run, what kind of software to use, what kind of data to collect, there are just so many decisions, and that forking of paths lead to different kind of analysis. There are just so many analysis which get done, and then you pick the best. And the thing is that if you have 100 different decisions made, chances are 5 of them would be incorrect. In that case, you would wrongly reject the null hypothesis. And the dilemma is that in the publications, they tend to only publish results which show some impact of one variable on another, which is statistically significant. And this leads to a lot of studies which were very foolish and sometimes unbelievable. For example, there was a study which showed that there is a statistically significant impact. If you listen to the songs of Beatles, that I Am 64, then it can actually help you feel younger. And there are a lot of other very nonsensical things published. But the thing is that to get published, you have to get something which shows that there is a positive relation, which is statistically significant. The thing is that if another person finds that there is no statistically significant relationship between the same things, that publication will not get published. And that because of this, a lot of things get published which are not factually correct. One solution which a lot of people are suggesting is that you pre-register what kind of analysis you're going to do, what is your hypothesis, and then you do the research. And only if you find something which is statistically significant, then you report it. It is similar to that when you are playing a game of pool and you have to pocket the ball, you have to tell in which pocket you are going to pocket the ball first, so that if the ball by chance goes into any other pocket, then you would know that it was just a coincidence. So if you tell beforehand that this is a pocket in which I'm going to pocket this ball, then there is lesser chance that that can happen just by coincidence. So the same logic applies here, that if you pre-register that this is my hypothesis, this is the data, this is the kind of analysis I'm going to do, and then report back results, if you find something statistically significant, then that is going to be much more trustworthy. Because the other option is that you keep testing a lot of things, and the chances are the 100 things you test, 5 of them you wrongly would say that they are statistically significant, and then you just report one of them. And the publications, they are incentivized to report something which is statistically significant relationship between two things, and then they just keep publishing it. And even if someone approaches them that they have done the similar kind of analysis on the same variables, but the results were not statistically significant, they will not publish that. Which means that when the next generation of the researchers will look at the published research, they will only find things which were considered statistically significantly related with each other, and which might actually not be the case. So be very mindful when you are looking at published research. Unfortunately, a lot of that is actually not correct. And as a data scientist, we must hold ourselves to this standard. Whenever we are publishing research or we are reporting back results to our stakeholders, we should not torture the data enough that it confesses whatever we want it to confess, because that is the case. If you try to do so many experiments, a lot of them would turn out to be statistically significant, which is just not the case. So now let's talk about another scenario where you can do the randomization, but simple randomization is not enough. So let's talk about some of the advanced techniques you have available then, so that you could introduce them to make sure that the results you're going to get out of that experiment are legitimate. So one is stratified randomization. So basically, you create different strata. It could be based off age, based off gender, based off location, and then from that, you pick the random samples. For example, if you're trying to survey people from a fitness app, there is a good likelihood that if you just randomly sample, it's possible that you just sample people who are young enough or who are healthy enough. It's better that you first segment people into the subgroups and then you do the randomization. A similar approach is blocking. It's just that it happens by nature. For example, if you want to see that what is the impact of different kind of
fertilizer on the land, then if you were to sprinkle that different kind of fertilizer on different kind of lands, it's possible that the results you see are because of difference in the land itself. So it's better that in the same chunk of land, try different fertilizers so that the differences you see there are because of the fertilizer itself and not because of the land. Another important technique is matched pair. That is when you want to introduce some change, you make sure that anything which you're putting in the control variable, you also have something similar in the test variable as well. And I think companies like Uber do that. When they try to increase the price in the test set, if they increase the price for certain kind of rider, then they try to find a similar kind of rider in the control group and make sure that the price is not increased for them. And then they try to see that what is the impact on different things for the same kind of matched pairs. And then there is sequential testing, basically similar to the multi-arm bandit theory, that you can stop early for clear winners or losers as you are running the experiments. You don't have to really wait till the very end. So what should your protocol or plan of action should be if you find some correlation in two things? First of all, look for confounders. For example, if you see that shark attacks and ice cream sales are very highly correlated, then you should not jump to the conclusion and first figure out if there is anything above them which is controlling both of them, confounders. So figure out if there are any confounders and then try to control them and then see. The second approach you should have is design an experiment and see that if you could randomly assign people to different treatment, then does that relationship exist if you have a random control trial, also known as RCT. So that is a gold standard. If you could do that, that is probably the best thing you should do. Just make sure you're doing the sampling intelligently. Make sure that you are getting good enough samples that you can have a statistically significant conclusion. If you cannot run experiment because you cannot assign the outcome randomly to people, for example, if you're trying to see what is the impact of smoking, in that case, you have to rely on some of the techniques which we previously covered. For example, you have to figure out if there were any natural experiments happening. For example, if one state banned one product and the other state did not. So that is a natural experiment. Then you can see what is the impact of one on the other. And there are other techniques, like we looked at instrument variables, we looked at differences. We also learned about regression discontinuity design. So see that what kind of other causal inference techniques you can use if you cannot run the randomized control trial. If you are still uncertain, then look for other approaches. Sometimes you need observational study as well as experiment, as well as some causal inference studies, all pointing in the same direction, just to make sure that the results you are drawing, especially if they are not very intuitive and expected results, just make sure that you go through all these routes. You first figure out the observational study. The good thing about observational studies is that you do not need to run any experiments. You just look at the data and draw some conclusions. But there are possibilities of faults there. That's why you have the gold standard is that you run some controlled experiments. And then there are some other causal inference observational studies which you can do. So try to do all of them, multiple of them, and then see that what the data is telling, and then only believe when multiple signals are pointing in the same direction. So now let's talk about some of the popular interview questions related to this. And these interview questions are more tricky and more nuanced than the ones we covered before, because there are a lot of right answers and it's sort of an open debate rather than a to-the-point actual answer which the interviewer might be looking at. So let's say if the question you get is users who engage with feature X, it could be any feature, we have seen that they have higher retention. Does it mean we should push that feature to everyone? Now, the naive answer would be that yes, of course, if it is shown that this feature usage is correlated with higher retention, then of course you should roll it out to more users so that there is higher retention overall. But a better answer is that we should not jump to the conclusion, because it's possible that there is a confounder here. For example, people who are more advanced users tend to use advanced features, and those advanced feature users tend to have high retention. So it's basically the confounder is the advanced usage. So advanced usage, it impacts our retention, and it also impacts advanced features usage. So it's possible that there is this advanced users, this is the confounding variable, and that is resulting in both, and you are wrongly drawing the conclusion that this is leading to this, which is clearly not the case. And it could be the case, but you first have to rule it out. How can you rule it out? Well, you have to rely on some instrument variables. For example, you can say, okay, let us randomly roll out this feature to some users and then see that what is their impact. Does their churn rate significantly changes from before or not? So you have to do that kind of technique to rule it out that this is the confounder which is impacting both of these. The next question is, we can't randomize pricing to existing customers. How do we know there is price sensitivity? So one clear option is that you roll out different pricing to different customers and then see if the lower price is converting more or not. So you can test price sensitivity like that. But if you cannot do that, then what are our options? Well, some of the options is that we take some days and then on those days we change the price and then see that does our sales increase or decrease on those days or not. Another option is that we have two different geographical areas, and then in one geographical area we change the price, in the other one we do not, and then see what is the impact on the number of sales. Another option is that we can look at some of the competitors. If they have ever increased the price or decreased the price, what has been the impact on sales? So we can use that kind of information to see that if the price sensitivity exists in our customer base or not. The next question is that our premium plan has lower satisfaction score. What might explain this? And another variation could be that the CEO, because of this, wants to get rid of the premium plan. What do you think about that? So in this case, again, we have to see that maybe the premium users, they are more intense users, and hence their expectations are higher than other free tier users or low tier users, and that is why their satisfaction is lower. And it's possible that Simpson's paradox is at play here, because we have to look at the data closely. It's possible that there are certain features which only premium users are using, and within that there is lower satisfaction rate, whereas in the rest there are better satisfaction rates. So your approach should be that first you find all the possible segments. It could be geographical region, it could be the use cases, it could be what is the company size, etc. if it's a B2B company. Then within each segment you try to see what is the satisfaction rate between the premium users versus the low tier users, and then see where are the differences. It's possible that premium users are using some of the features or are using it for some of the use cases which other users are not using, and that is what has the lower satisfaction score. So again, there is no clear right or wrong answer. It's just that we have to do a lot more data investigation to draw some conclusions out of this. And lastly, they can ask you to create a causal diagram between different features. For example, user behavior, features, outcome, how are they all related? What are the arrows going into different direction? What is impacting what? And then based on that, you might be asked to understand what are the confounders? What are the colliders in this diagram? And what are the factors you should be controlling for? Again, confounders are something you should always be controlling for. So these are some popular interview questions which are related to this module. Next, we are going to see Simpson's paradox in practice in the lab. Yeah, so I used Claude to create this a sample case study to illustrate Simpson's paradox. So the case here is that we have a data of about 100 coffee stores, and 60 of them are in downtown, mostly play jazz music. 40 of them are in suburban area, they mostly play pop music. Downtown stores naturally have higher revenue, And we want to see that if there is an impact on what kind of music is played on the sales which happen. So this is a synthetic data generated. Let me click this. The data is generated. Okay. So if we were to do a very naive kind of analysis, you can see that there are 42 stores in downtown, 52 in urban, 41 have jazz music, 59 have pop music. Now, if we were to do a naive analysis, we would see that stores which are playing jazz music, they have more revenue on average than stores which are playing pop music. Now, from this, the naive analysis would draw that more stores should play jazz music because that leads to increase in revenue. And this is a basic analysis. You can see that the difference is 25.9% higher for jazz, much higher. And the p-value, look at the p-value, it's a 0.002. There is 0.02% chance that you could see this result by chance if the kind of music which gets played had no impact on sales, on revenue, which is the null hypothesis. Okay. So the case is closed. Jazz earns 23% more. So we should definitely switch to jazz for all stores, right? Well, not so fast. Let's look more closely. So when we look at revenue by location, again, the Simpson paradox, when you look at the data aggregated, it tells you a different story. But when you look at each segment, then you see what's going on. So when we look at the data closely, we see that the downtown stores tend to have much more revenue because of their location. And within each location, we see that though jazz is still higher, but the difference is much smaller. So now let's try to look at things overall and within group. So overall, we see jazz is much higher, but within downtown and suburban, the difference is very small and very subtle. So we need to do some sort of experimentation, some sort of power analysis. So let's do power analysis to see how many stores do we need to randomly pick from both of these groups to see if the results are actually statistically significant or not. So our current revenue is 5,000. Standard deviation is 1,000. Meaningful difference would be 5%, which is $250 per day. And desired power is 80% with significance level of 0.05, which means basically 95% of confidence. So let's see what the calculation turns out to be for sample size. So if we want to detect 5%, then we need 251 samples from each group. And this is the whole chart. As if we want 4%, then we need more samples. But let's settle with 251 and then randomly pick 251 stores from each bucket. And now when we see, now this sort of eliminates the impact of location because it is a stratified randomization. So we can see that the difference again here is very subtle. And let's analyze the randomized results. Now when we see this represents the confidence in the prediction interval. And as you can see, now the results are almost similar, especially when you look at the standard deviation. And let's look at the p-value here. Now the p-value is much bigger, which means the results are insignificant. There's no significant impact of music on revenue when we look this closely. Now let's look at the interaction effect. Again, there's very minimal interaction, if any. Let's do some advanced analysis on this. So let's say there was a licensing change. And some of the stores, 15 stores, were forced to use pop music instead of jazz. So let's see what happened there. Average revenue after switch was this. So for the stores which transition from jazz to pop, this is their revenue. And for the stores which kept jazz, this is their revenue. And this is identical, which means there is actually no impact at all. And now let's do regression analysis. So how we do regression analysis, something which we're going to cover in our series on machine learning. But the equation basically translates into what is the impact of each of these factors, what is the impact of music, what is the impact of location. We can see that the impact of music is just $75, whereas impact of location is much higher. So the interpretation is that after controlling for location, jazz music only adds $75 to revenue. And location adds $1,400, and which basically means that even if there is a little impact of playing jazz on revenue, it's very little. So if we were to create an executive summary, it'll be something we like. The initial findings said 23%, but when we look closely, it is very small, essentially zero, minus 47 to 123. And location is something which highly impacted. And based on this, we do not recommend that stores change the kind of music they're playing from pop to jazz, because as we initially mistakenly understood, that it leads to increase in revenue by 23%. So I hope this lab helps you understand that how easy it is to be deceived by the data when you're looking at the collective aggregated data. And hence, it is very important that you look at the data closely into different aspects of it, different dimensions of it closely to see what's going on before you draw any conclusions. All right, so what did we cover in this module? We covered a lot. We first figured out why correlation does not always mean causation. And even when it is, then what kind of analysis you should be doing and how cautious you should be before you start drawing some conclusions. We looked at Simpson's paradox and the kind of third variables or other variables you should be considering before you draw the conclusions, because when you are looking at the data holistically, it's possible that you're seeing the wrong picture. You have to look at the other factors, other confounders, before you get the real picture. And then we explored experimental design principles and how you can use power analysis to basically figure out how you can draw the causal relationship between different variables in a statistically robust way. This was a long module. I hope that the lessons you learned here are valuable for you, especially as you appear in the interviews. Most of these things will help you explain the situation, explain the scenario, especially when you are talking about different real world business case studies. This is the kind of knowledge you need to better explain your chain of thought when you are talking with the interviewer. So I hope this was helpful, and I'll see you in the next module. Cool. As we are approaching towards the end of this course, I wanted to cover a very important brief introduction about two different school of thoughts in statistics, which is Bayesian versus frequentist school of thoughts in statistics. So in this module, we are going to see that how these two major school of thoughts differ. We'll go through a very interesting story about how Alan Turing cracked the Enigma code, which was basically an encryption machine used by a German Nazi. And then we'll see what are the key concepts which are contrasting frequentist versus Bayesian approaches. And then how do both of them reason with uncertainty? So it's going to be a very quick module. So let's jump right into it. So let's start with the story of Enigma machine. So Enigma was basically a machine which used to encrypt the messages. So if this is the incoming actual message, then this machine will encrypt it so that the encrypted message is something which is unable to be read by other people. And German Nazi used to use this machine for encrypting their messages, and it was trusted to be so secure that even their top most secret conversation, they used to encrypt it through this. And the reason this was so much trustworthy for them was that there were a total of 1.59 to the power of 1020 combinations of settings which this Enigma machine could have. Now, this number is so large that if you find all the atoms in the entire Earth, this number is even bigger than that. So there is no way that someone could crack the code of what is the exact combination which is used to encrypt these messages. And on top of that, they used to change the setting every day. And every day they would communicate, the German forces would communicate what is the setting for the day for the machine. And then with every message, some new setting would also be passed on. So the daily setting plus the message setting along with the message has to be passed into this machine to get the encrypted message. Or if you pass in the encrypted message, it used to work both ways. Then you get the actual human readable message. So finding what the actual setting is so that you could use it to decrypt the messages was, even that kind of computer is not available even today. And we are talking about World War II. So about a century ago, this was definitely not possible. And later in the module, we'll see that how Alan Turing used Bayesian mindset to crack this almost impossible task. So when we are talking about frequentist versus Bayesian approach, let's start with frequentist school of thought. What do they actually think and how do they process information? So in frequentist school of thought, when they say probability is basically a long-run frequency of an event. So when they say that the probability of having a head in a fair coin is 0.5, it basically means that if you run this trial for very, very long period of time, this is the frequency towards which this will emerge. And then parameters are fixed but unknown constants. So any parameter of the population, for example, if you're talking about what is the average height of a US male adult, an unknown constant, but it is a fixed constant. You don't know about it, but whatever that value is, that is a fixed value. This is what frequentists think. And then the data is a random sample from the population, and then p-value, confidence intervals, hypothesis testing, all those terms which we covered in the previous modules. This is all the thinking and the mindset of the frequentist school of thought. Now let's quickly see how does Bayesian think about this information. So Bayesian school of thought is slightly different. When they think about probability, they say that probability is your reasonable belief at a time. And that is subject to change based on as you see new information. So even when they say that the probability of having a head in a fair of coin, they would still say, yeah, it is 0.5, but it is subject to change. This is what we currently believe, but as we see more evidence, we might change it. And the core idea is that we can and we should update our belief. Any assumption, any understanding, any probability is not something to be taken for granted. As we get more information, our beliefs are supposed to be changed. So we start with a prior probability about what our prior understanding of the world is. Then we gather the data, and then we get posterior probability. We update our probability constantly. And the parameters themselves have probability distribution. For example, when we are talking about, again, male average height in the US male adults, then that's not a single number. It's actually a probability distribution. And it can lie anywhere between that range. So this is how Bayesian school of thought think about these things. So now let's look at how the Bayes theorem works. We already covered it in the past, but a quick recap. So this is the formula, and we start with what our prior belief is. So that is P of A, that is your initial hypothesis strength. And then probably B of A is that how likely is the new evidence. And then based on that, you are constantly update your belief, which is probability of A given B, and you keep updating your beliefs based on what new information you are seeing. So don't spend too much time understanding and trying to memorize the formula. The key thing is that based on the new information, you keep updating your prior beliefs as the new data unfolds. So let's see that how Alan Turing cracked the impossible Enigma machine using Bayesian thinking. So Alan Turing definitely realized that you cannot just brute force your way into figuring out what is the right setting. But he said that we can use some hints, and based on that, we can update our beliefs about what is the more likely setting than others. And the information which he was using to update his beliefs was called cribs. What is a crib? He basically found a lot of German messages. So he found, for example, this is the German encoded message. And then he knew that these messages will have some known phrases. For example, they will start with Hail Hitler. They would mention something about weather. So he had those clues. And then he knew that once that information gets passed into the Enigma machine, what is the expected output? For example, if it is Hail Hitler. So then he tried a lot of those combinations into the input and then see at which value they started giving the expected output results. And based on that, he kept narrowing down the possible list of actual settings. And he used a machine which was called the bomb, which used to test a lot of these beliefs as quickly as possible so that he could narrow down the total number of possible settings which can be used to crack the Enigma code. And that's the Bayesian thinking which led him to crack that machine. And because they were able to crack that Enigma machine, they were able to decrypt a lot of German communication. And that led to actually concluding World War II much earlier than people were forecasting. So at a high level, what is the summary in terms of differences? So when it comes to probability, Bayesian think that it is a belief about what the reality is, and that belief is subject to change. Whereas frequentists think that it is a long-run frequency. It is a characteristic or a property of that thing. For example, it is a property of the coin that if you flip it enough time, on average, you would be seeing 50% of the heads. Whereas in Bayesian school of thought, they think it's just a belief which can change. Parameters, frequentists think that these are fixed but unknown constants. For example, as I said, what is the average height of male in the US? It is unknown, but that is a fixed thing. Whatever it is fixed. That is what frequentists think. Whereas Bayesian think that these are random variables which have their own probability distribution, and there's no real one answer. It is something which exists and which is subject to change as well. And then in terms of inputs, Bayesian incorporate prior knowledge and then keep updating their belief as they get the new data. Whereas frequentist school of thought, as we have gone through a lot of hypothesis testing, p-value, t-test, all of that, they just look at the data alone and then based on that they make the inference. And the final output is that in Bayesian statistics you get the probability distribution of whatever you're trying to pinpoint. Whereas in the frequentist world, you get a point estimate and then an interval around it. For example, they would say that the average height of male in the US is 5 feet 10 inches, and the 95% confidence interval around it is, for example, 5 feet 6 inches to all the way to 6 feet. So at a high level, this is how these two schools of thoughts differ. Now, to quickly conclude the module, let's recap what we covered. So we covered the two main philosophies of statistical thoughts, both Bayesian and frequentist school of thoughts. We saw that how Bayesian thinking led to cracking the Enigma code, which was an impossible task if we have to adopt the frequentist mindset. And this also tells us that neither of these approaches are inherently right or wrong. These are two different ways of approaching the same problem. And if one approach is giving you a hard time, try the other one. You should have both approaches in your repertoire. Then what is the core difference between these two? How they treat probability and how they treat prior information. So that was all for this module. I intentionally kept it very short and to the point. And in the next module, we are going to see what are some of the most popular interview questions which get asked throughout statistics for the data science roles, and We'll try to answer those questions based on all the learnings we had done in the 8 modules so far. I hope you find the content so far useful, and I'll be looking at you in the next module.